Is there a scientific theory that sounds almost ridiculous the first time you hear it? Science has a long history of ideas that were once dismissed as absurd until evidence slowly forced us to take them seriously. Black holes themselves were mocked for decades. The Big Bang was once considered speculative. Even the idea that space and time could bend seemed unreasonable when it was first proposed. And yet, today, these ideas form the backbone of modern physics. There is one hypothesis that still sits in this uncomfortable space between skepticism and possibility: the idea that our universe may exist inside a black hole. At first glance, it sounds like science fiction, but this is not a fringe fantasy or a late-night thought experiment. Versions of this idea have been debated for years by physicists working in general relativity, quantum theory, and higher dimensional cosmology. They arise not from imagination, but from trying to understand what happens at the extreme limits of gravity, time, and information. What if the Big Bang was not the ultimate beginning, but the internal outcome of a collapse in a larger reality? What if our expanding universe is what space looks like from the inside of a black hole? Exploring this possibility forces us to confront uncomfortable questions about the nature of reality, the fate of information, and whether black holes are truly cosmic graves, or something far more profound. Stay with this idea, not because it is proven, but because questioning it may change how you understand the universe itself. The idea hangs in the air for a moment, like the afterimage of a bright flash behind your eyes, refusing to fully disappear. If the universe might be the inside of something else, then even our most familiar story about its beginning starts to feel strangely incomplete. You probably carry a picture of that beginning, even if you have never tried to draw it. A tiny point, a sudden burst. Darkness torn open by a blinding explosion that sends matter racing outward into empty space. It is a vivid scene. It feels cinematic. It feels understandable. And almost every part of it is wrong, or at least deeply misleading. In the standard story of cosmology, the Big Bang is not an explosion in space. It is an expansion of space. There is no quiet vacuum sitting outside, waiting to be filled. There is no center where everything started, and no edge where the blast is still arriving. Every region of the universe was once closer to every other region. Space itself has been stretching, carrying galaxies apart, the way dots drawn on the surface of an inflating balloon drift away from one another, even though none of them is at the center of the surface. Seen this way, the Big Bang is less like a firework going off somewhere and more like an everywhere event, a change in the state of the whole universe. And yet, even this cleaner description hides a deeper unease. When we say the universe began in a hot, dense state and has been expanding for billions of years, we sound as if we understand the beginning. We do not. What the equations of general relativity actually tell us is something more narrow and more unsettling. If we take the current expansion of the universe, roll the film backward, and follow the rules of gravity encoded in Einstein's theory, distances between galaxies shrink, temperatures rise, densities increase. Extrapolated far enough, the math predicts that, in the finite past, everything we see was once compressed into a state of effectively infinite density, a singularity. A singularity is not a point we can picture. It is not a tiny marble of matter hanging in a pre-existing void. It is a place where the theory itself breaks, a signal that the rules we are using are no longer sufficient. When we say the universe began there, what we really mean is that, beyond that point, our current equations stop being reliable. It is the edge of a map, labeled not with a clean, "Here lies the origin," but with a quiet warning. Beyond this, you do not know. And yet, We talk about this edge as if it were a true beginning, as if time itself suddenly switched on like a light, as if before this singularity, there was not only no matter, no space, no fields, but also no before at all. This is where the story begins to tremble. Our minds like beginnings. We grow up inside narratives. We ask for the first chapter, the first cause, the first moment. Even when we accept that the Big Bang was not an explosion in space, we still instinctively treat it as the first frame of the universe's film. The origin shot, the place where the story starts. But physics does not promise that such a frame exists in the way we imagine. In everyday life, when we speak of a beginning, we imagine something outside the story watching it start. A reader opening a book, a camera that was idle before it started recording, a clock ticking long before the scene it measures. Our language smuggles in an external vantage point, a time that exists beyond the time of the story, a space outside the space we are describing. When cosmologists say time begins at the Big Bang, they are not secretly imagining some earlier clock that we are not allowed to talk about. They are saying something stranger. They are saying that the parameter we call cosmic time, which orders events in our universe, cannot be extended indefinitely into the past without the theory losing its meaning. But this is about the internal logic of the model, not about a godlike observer watching nothing suddenly become something. The 14 piece us, if there is no outside clock, then what does it really mean to ask what happened before the universe? And if we cannot even define before in the usual way, what does it mean to insist that the Big Bang is the absolute beginning? Here, a quiet possibility appears. It does not shout. It does not claim certainty. It just asks whether our insistence on a clean beginning is a reflection of the universe or of us. Einstein's equations do not only describe expanding universes, they also describe the collapse of massive objects under their own gravity. And when that collapse is extreme enough, they give us another kind of singularity, the one at the heart of a black hole. Just as we can run the film of cosmic expansion backwards toward a dense initial state, we can run the film of gravitational collapse forward, watching a star shrink, cross a critical threshold, and continue inward toward a region where known physics breaks down. In both stories, the same mathematical framework is whispering something similar. Push gravity far enough, and space-time itself stops behaving in ways our current theories can track. We hit an edge, not of reality, but of description. Some researchers have wondered whether these two edges might be related. If the Big Bang singularity is where our model of an expanding universe fails, and a black hole singularity is where our model of a collapsing star fails, then perhaps both are hints of a deeper process. Something that turns collapse in one context into expansion in another. Something that, from one vantage point, looks like the end of a star, and from another, looks like the birth of a universe. This is the core provocation hiding behind the simple phrase, our universe could be inside a black hole. Not that we are swirling around near some central point, waiting to be crushed, but that what we call the beginning of our cosmic story might be the internal continuation of a collapse occurring in a larger, unobserved reality. Notice how quickly our intuition tries to draw a picture. A bigger universe out there, a massive star in that universe, collapsing, a black hole forming, and inside that black hole, our universe blooming into existence, its space expanding, its galaxies condensing out of hot plasma, its time ticking forward from what we call the Big Bang. It is a satisfying image. It feels like an explanation, but every part of that internal picture is stitched from metaphors, not direct observation. We do not see the outside. We do not track the collapse from a safe distance. We are, if this idea is even approximately right, like creatures that evolved inside a sealed room, trying to infer the architecture of the building from the drafts under the door. From within our universe, we measure only internal relationships. How long light takes to travel between galaxies. How clocks tick in different gravitational fields. How the cosmic expansion changes over time. The Big Bang, in this sense, is not a visible fireball on the horizon of reality. It is an inference drawn from patterns inside the room. This makes the question of beginnings even more delicate. When we say that the universe started in a particular way, we are extrapolating from observations we can make only now, in our present cosmic era, after billions of years of expansion have already passed. We are reconstructing an origin from traces, the faint afterglow of the early universe. The distribution of galaxies, the relative abundance of light elements. It is an impressive reconstruction. It works remarkably well, but it is built entirely from clues available within our own horizon. The spherical limit set by how far light has had time to travel since the Big Bang. That horizon is not a wall of matter. It is not a shell of stuff surrounding us. It is simply the boundary between events that have had enough time to send us light and events that have not. Beyond that distance, the universe may continue, or it may change, or it may connect to regions we cannot meaningfully describe. Our theories extend beyond the horizon with confidence, but our data do not. We are extending the map past the last place we have actually seen. This is not a flaw in cosmology. It is a condition of doing cosmology from inside the universe. Any creature that lives in a space-time with a finite age and a finite speed of light is going to face this limitation. There will always be regions that cannot be observed yet, or ever. There will always be edges of inference. Now, the analogy with a black hole begins to sharpen, not as a dramatic claim, but as a question about perspective. A black hole has an event horizon, a boundary in space-time that divides events that can still influence the outside from events that never will. Once something crosses that horizon, light emitted from it can no longer escape to distant observers, to someone far away. The horizon is a limit of information, a place beyond which the story cannot be followed. Our universe has its own horizons, not just the event horizon of any particular black hole, but cosmic horizons tied to expansion and to the finite age of the cosmos, regions we will never see, no matter how long we wait, because space is stretching too quickly, or because light simply has not had enough time to reach us and never will. From a certain vantage point, the entire observable universe looks like the interior of one of these information-limited regions, a finite bubble inside a larger, perhaps infinite, structure. If we allow ourselves to lean into that analogy, without demanding that it be exact, a new way of phrasing the Big Bang appears. Not the moment when everything began, but the inner face of a boundary we do not fully understand. Perhaps what we call the origin is, in some wider geometry, the continuation of something else. Perhaps the singularity at the start of our equations corresponds to a surface we cannot see, the inner side of a collapse happening beyond our horizon. None of this replaces the standard cosmological model. That model remains astonishingly successful at describing how the universe evolves after it is already hot, dense, and expanding. But it shifts the emotional weight of the question. Instead of asking why did something come from nothing at that exact instant, we begin to ask, what is the larger process, if any, in which this hot, dense beginning is just one phase? Okay, to trace that thought any further, we need to understand black holes not as pop culture monsters, but as precise solutions to the same equations that describe the expansion of the cosmos. We need to examine their boundaries, their horizons, and the strange way time and space behave near them. Only then can we meaningfully ask whether the story we tell about the universe's birth is simply a special case of a more general pattern written into gravity itself. The thought that our own beginning might be the inside of something else quietly pushes us toward a different question. How did we even come to believe that such extreme objects as black holes could exist at all? Long before the term black hole was spoken, people were already wondering how far gravity could go if you let it. In the late 18th century, when Newton's picture of gravity as an invisible pull between masses still reigned, a few thinkers pushed that picture to its edge. One of them, a clergyman and scientist named John Michell, imagined a star so dense and with gravity so strong that even light trying to escape from its surface would be dragged back. He called them dark stars, not because space itself was strange, but because the light could never get out. To understand why this matters, it helps to slow down and feel what gravity meant at that time. Gravity was seen as a force that acts at a distance. You do not need anything in between. Two objects simply attract each other according to their masses and how far apart they are. If you throw a stone, gravity pulls it down. If you fire a cannonball faster, it travels farther before falling. The idea of escape velocity comes from this. Throw something fast enough, and it will never fall back. Now, stretch that idea. Imagine a surface where the speed required to escape is so high that even light, which people already suspected to be the fastest thing there is, cannot reach it. Michell's reasoning was simple and radical. If light behaves like small particles shot outward from a star, and if gravity pulls on those particles, then there is a threshold where gravity wins. A star could be massive enough and compact enough that its escape velocity exceeds the speed of light. From far away, that star would be invisible. Its presence would be known only through its gravitational influence. For his time, this was an almost absurd suggestion. It made no dent in everyday astronomy. There were no telescopes able to test it. No instruments capable of revealing invisible giants by their pull. Another thinker, Pierre-Simon Laplace, came to similar conclusions and then quietly stepped back from them. The idea was too speculative, too disconnected from measurable phenomena. It lived as a curiosity at the margins of theory, a strange possibility whispered by equations that no one quite knew what to do with. The universe, as most people imagined it, was still a grand mechanical clock, its parts visible and well-behaved. Dark stars were a clever trick of algebra, not something the sky would actually contain. Everything changed when gravity itself was reimagined. In the early 20th century, Einstein proposed general relativity, and with it, a new way of thinking. Gravity was no longer a force acting across empty space. Instead, matter and energy tell space and time how to curve. And that curved space-time tells matter how to move. This is the essence of general relativity, not an extra push pulling things together, but a reshaping of the stage on which motion happens. If that sounds abstract, think of a heavy ball placed on a stretched rubber sheet. The sheet sinks around the ball, and smaller objects rolling nearby follow curved paths. They are not being pulled by an invisible string. They are simply following the shape of the surface. In Einstein's picture, massive objects deform space-time, the way the ball deforms the sheet. Planets orbit stars not because they are tugged along by a force, but because they are moving along the natural paths in a curved geometry. Once you adopt this view, the question of how strong gravity can become is a question about how sharply space-time can bend around mass and energy. And here, the story takes a stark turn. Very soon after Einstein wrote down his field equations, another mind pushed them to an extreme. In the same way, Michell had once pushed Newton's law. Carl Schwarzschild, working under brutal conditions, found a precise solution to Einstein's equations that describes the space-time around a perfectly spherical, non-rotating mass. Embedded in that solution is a critical radius, a distance from the center, where something peculiar happens. If you compress a mass inside that radius, the geometry of space-time around it changes in such a way that not even light can escape from within that boundary. This threshold distance is what we now call the Schwarzschild radius. The surface at that radius is not made of any special substance. It is not a physical shell. It is a geometric boundary in space-time, a point of no return for light and matter. Cross it heading inward, and all possible paths you can follow, even if you travel at the speed of light, lead deeper in. From the outside, this boundary would mark the edge of a region from which no information can emerge. Much later, this would be named the event horizon. For a while, even with this exact solution in hand, many physicists regarded such objects as mathematical oddities. The idea that a star could actually collapse within its own Schwarzschild radius and form a region cut off from the rest of the universe seemed outrageous. There were attempts to argue that some internal pressure or unknown mechanism would always prevent complete collapse. The singularities predicted deep inside these solutions were especially troubling, places where curvature becomes infinite and the equations fail. It felt like a sign that the theory should not be trusted in those regimes, rather than a literal description of nature. Yet the equations were stubborn, again and again. More general solutions and more careful analyses showed that, under realistic conditions, massive stars with no way to support themselves against gravity would indeed continue collapsing. They would overshoot any hypothetical safe state and cross their own event horizon. The formation of black holes stopped looking like a pathological exception and started to appear as a natural outcome of gravitational collapse. Still, for decades, these objects remained ghosts in the mathematics. The sky did not obviously present us with completely dark, compact masses. Telescopes saw stars, nebulae, galaxies. They saw supernova explosions, gas clouds lit by newborn stars, slow drifts of galaxies across the cosmic web. To turn black holes from speculative creatures into scientific objects, we needed a different way of seeing. The key was to focus not on the invisible interior, but on the way matter behaves as it falls toward the unseen boundary. Imagine gas spiraling into a massive, compact object. It does not fall straight in. It forms a disk, swirling around, rubbing against itself, heating up through friction and compression. This glowing structure is called an accretion disk. Near a black hole, such a disk can reach temperatures so high that it radiates intensely in X-rays and other energetic wavelengths that our eyes cannot see, but our instruments can. Astronomers began to find binary systems where a visible star orbits an unseen companion that is too massive, too compact, and too dark to be an ordinary star, or even a dense stellar remnant like a neutron star. The behavior of the bright companion, the pattern of X-ray emission from surrounding gas, the inferred mass of the invisible partner. All of these clues converged on the same picture. The most straightforward explanation was that these systems contained black holes. One of the first convincing cases involved a system whose X-ray flickers and orbital dynamics matched what would be expected if a massive, invisible object were feeding on material from a nearby star. It was not just a clever story. It was a model that fit the data better than its rivals. Slowly, skepticism softened. Black holes were no longer just extreme possibilities permitted by general relativity. They were becoming part of the observed inventory of the universe. As observations improved, the scale of the story expanded. At the centers of many galaxies, including our own Milky Way, evidence grew for the presence of black holes millions or even billions of times more massive than the Sun. These are the supermassive black holes. They are surrounded, in some cases, by whirling gas and dust, and by jets of particles streaming out at nearly the speed of light. Entire galaxies seem to be shaped, at least in part, by the activity near these central giants. This shift from skepticism to reluctant acceptance to active exploration matters for our larger question. It shows how ideas can migrate from the edge of plausibility to the core of our understanding, not through belief, but through the steady pressure of evidence and coherent theory. What began as an almost absurd consequence of pushing gravity to its limits has become a central feature of modern astrophysics. It also reveals something about our relationship to extreme concepts. For a long time, the notion of an object from which light cannot escape felt too strange to be real. It was easier to file it away as a mathematical curiosity. Only when technology advanced enough to capture the indirect signs of these objects did we begin to accept that the universe might be stranger than our comfort allowed. Now, black holes sit at a curious intersection. They are, on the one hand, well described in many respects. We can predict how matter orbits them, how light bends around them, how their presence influences nearby stars. On the other hand, their interiors remain hidden behind horizons, and the singularities predicted by classical general relativity still mark regions where our understanding breaks down. They are both familiar and fundamentally opaque. This is the landscape in which the hypothesis that our universe might be related to a black hole interior arises, not from science fiction, but from a theory that has already forced us to accept entities once thought impossible. To go further, we need to look more closely at what happens as gravity tightens its grip, at the boundaries black holes create, and at the regions beyond those boundaries that no outside observer can ever see. At some point, if we take these boundaries seriously, we have to ask a harder question. What does it really mean for a region of space-time to be sealed off? Not by walls, but by the way reality itself is curved? In the early days of general relativity, that question was not yet framed in such dramatic terms. Einstein had written his field equation, but the full range of their consequences was still hidden. These equations relate how matter and energy shape space-time to how space-time, in turn, guides motion. They are difficult to solve in general, so physicists began, as they often do, with special cases, simple situations, symmetric worlds. Carl Schwarzschild was one of the first to push directly into the gravitational deep end. He asked a focused question: what is the exact shape of space-time around a perfectly spherical, non-rotating mass that is not changing with time? No explosions, no spinning, no complications. Just a static, spherical object sitting in an otherwise empty universe. This sounds like a toy problem, a stripped-down, almost boring case. But sometimes the simplest questions cut the deepest. When Schwarzschild worked through Einstein's equations under these assumptions, he found a very specific description of the geometry around such a mass. Hidden inside that description was a particular distance from the center where the mathematical form of the solution behaved oddly. At that radius, certain quantities seemed to blow up. It looked, at first glance, like a singularity, a place where the theory breaks. For a while, many took this at face value. They assumed that this troubling behavior signaled some physical edge, some literal obstacle sitting at that distance. But as the solution was studied more carefully, a different picture emerged. The strange behavior at that radius turned out not to be a genuine tear in space-time, but a problem with the coordinates used to describe it. The way a map can show the Earth's poles as stretched lines, even though the planet itself is smooth. Still, that radius was not an illusion. It marked something real. If you compress a mass into a sphere whose surface lies inside that critical distance, the structure of space-time around it changes in a dramatic and irreversible way. This critical distance is what we now call the Schwarzschild radius. For an object like our Sun, if you could somehow squeeze all of its mass into a sphere only a few kilometers across, the Schwarzschild radius would sit just outside that sphere. For Earth, the corresponding radius would be about the size of a marble. Those comparisons are rough. But the point is simple. Take enough mass, pack it tightly enough, and you cross a threshold where escape becomes impossible. The surface defined by this radius is what later generations named the event horizon. It is not a material shell, If you were falling in, you would not slam into a wall or see a sudden flash as you pass through. Locally, in your own immediate surroundings, nothing special would happen at that exact location. The horizon is a global feature. It is defined not by what you feel in that moment, but by what is possible from that point onward. To understand this intuitively, imagine space-time as a kind of flow, carrying everything forward. The paths that light can take at each point are like the directions a small boat could steer if it runs at its fastest speed relative to the water. Far from a massive object, the flow is gentle. The boat can always steer away, fight the current, and escape to distant regions. Closer in, the current strengthens. There comes a point where, even if the boat aims straight outward at maximum effort, the flow inward is so strong that it is dragged closer to the center anyway. The event horizon is the surface where this becomes inevitable. Outside it, there are still possible paths that lead outward to the wider universe. Inside it, all possible paths, even the ones following the maximum speed allowed by nature, lead further in. The phrase "point of no return" is not poetic exaggeration. It is a literal statement about the structure of causality. Once inside the horizon, you cannot send a signal that reaches someone who stays outside. The space of reachable futures has changed. From the viewpoint of a distant observer, the horizon has an even stranger character. If you watch an object fall toward a black hole, the light it emits on its way down becomes increasingly redshifted. That means its light is stretched to longer, redder wavelengths as it climbs out of the deep gravitational well. The object also appears to slow as it approaches the horizon. Its signals take longer and longer to reach you. In the limit, it seems to freeze, fading and stretching into darkness, never quite crossing the boundary in your frame of time. From the perspective of the falling object, however, there is no infinite delay. Its own clock ticks normally. It crosses the horizon in a finite time, continues inward, and reaches regions where the curvature of space-time becomes extreme. This contrast is not a contradiction. It is a reflection of how time and distance are intertwined differently for observers in different gravitational situations. In general relativity, there is no single, universal clock. Each path through space-time carries its own measure of duration. This is one of the first places where the intuition we carry from everyday life begins to fail. We like to think that if something happens, there should be a single, definite story about how long it took and where it occurred, independent of who is watching. Near an event horizon, that assumption dissolves. What is never quite in one frame is definitely already in another. The horizon is not just a boundary of escape, it is a boundary of shared description. When Schwarzschild's solution was first written down, the full implications of this boundary were not yet appreciated. It took decades, and the work of many others, to understand that the apparent singularity at the horizon could be removed by changing coordinates, while the singularity deep inside, at the center, could not. That central singularity, where the curvature truly diverges and the equations break, is the place where classical general relativity admits its own limits. The horizon, by contrast, is a smooth but unforgiving gate. Why does this matter for our wider story about the universe? Because the event horizon is the most precise example we have of a place where physics draws a line between what can be known from outside and what belongs irretrievably to an interior. Everything that crosses the horizon remains part of space-time. It has a future. It experiences events, but those events are sealed away from the external world. There is no experimental trick, no clever measurement, that can reveal the detailed history of what fell in. The horizon is a censorship of sorts, not by secrecy, but by geometry. It is here that the analogy with cosmology begins to sharpen. Our observable universe also has a kind of horizon, set not by collapse, but by expansion and finite age. There are regions of space-time that can never send signals to us, not because they are inside a black hole, but because the fabric of space between us and them is expanding too quickly, or because not enough time has passed for their light to arrive. The Big Bang singularity itself stands at the limit of what our current theory can describe, just as the central singularity of a black hole stands at the limit inside the horizon. In both cases, we have a structured interior, a boundary beyond which information cannot be retrieved, and an edge of theory where our equations fail. The Schwarzschild solution makes all of this explicit for a particular, highly symmetric case. It gives us a laboratory in the mind for thinking about points of no return. Once you see the horizon as more than a plot device, it begins to feel less like a monster's mouth and more like an epistemic wall, a limit on what can be known from a given vantage point. You start to notice how often our descriptions of the universe assume that no such walls exist. That, with better telescopes or more patience, we could in principle see everything. The event horizon quietly contradicts that assumption. It says, even with perfect instruments and infinite time, some regions are forever out of causal reach. This is the seed of the more radical thought to come. If the structure of gravity naturally produces such interior regions, separated from the outside by one-way boundaries, then it is not absurd to ask whether what we call the whole universe might itself be only an interior, seen from within. The Schwarzschild radius, in this sense, is not just a number associated with a mass. It is the radius of conceptual humility, the distance at which our confidence in an all-seeing perspective must collapse. To follow that possibility deeper, we will have to live, for a while, on the horizon's edge. We will have to think like observers who can never step outside the system they are studying. And that means taking seriously what it feels like to approach, and then cross, a point of no return. Before we imagine falling through such a boundary from the inside, we have to face a more down-to-earth question. How did something so abstract ever become part of our description of the real sky? For a long time, black holes lived only on paper and in arguments. They were the uncomfortable consequences of equations that many physicists tried not to look at too closely. The notion that nature would actually build one of these objects, that stars would really collapse past their own point of no return, felt almost indecent. The universe, in the common imagination, was dramatic but not obscene. Stars exploded. Planets formed. Nebulae glowed. But the idea of matter collapsing into darkness from which nothing returns seemed too extreme, like a story that had wandered beyond what reality would allow. What shifted that intuition was not a single dramatic event, but a slow tightening of evidence. Astronomers learned to see in parts of the spectrum our eyes ignore, telescopes that detect X-rays. A kind of very energetic light began to reveal sources scattered across the sky that were invisible in ordinary optical light. X-rays are usually emitted by matter at very high temperatures, so any point that shines brightly in X-rays is a clue that something violent is happening there. Some of these bright points turned out to be binary systems, pairs of stars orbiting around a common center of mass. In a few cases, only one member of the pair could be seen in visible light, while the other betrayed itself only through the behavior of gas spiraling toward it and the X-rays that gas emitted. A binary system is simple in concept. Two objects, bound by gravity, looping around each other. But when one partner is unseen and massive, the orbit of the visible star becomes a way to weigh the invisible one. By carefully tracking the motion of the visible star, astronomers could infer the mass of its dark companion. In some systems, that mass was too large to be a dense stellar remnant like a white dwarf, which is the compact core left behind when a smaller star sheds its outer layers, and too small and quiet to be a cluster of ordinary stars. The simplest explanation was that the invisible object was a black hole, a region whose Schwarzschild radius fell well outside the physical size needed to trap any light emitted near it. One famous case involved a source in the constellation Cygnus, an X-ray emitter whose behavior matched what would be expected if a normal star were feeding gas onto a compact, unseen partner. The pattern of the star's orbit and the intensity and variation of the X-rays from the surrounding gas together painted a consistent picture. Something heavy and dark was there, pulling, stripping, swallowing. Not a vague, conceptual singularity, but an object whose mass could be estimated, whose distance could be measured, whose effects could be monitored night after night. This was a turning point of a quiet kind. There was no single press conference when the universe officially admitted to containing black holes. There was instead a growing sense among working astronomers that, once you accepted general relativity, these objects were not optional. They were the best available explanation for what was being seen. The category of black hole candidate entered the language, always with some caution, but with increasing confidence that the candidates were not imposters. Around the same period, another development was unfolding at larger scales. At the centers of many galaxies, astronomers observed compact regions emitting enormous amounts of energy. Some of these central engines were incredibly bright, outshining all the stars in their host galaxy in certain wavelengths. Yet they were confined to a volume smaller than the orbit of the outer planets in our own solar system. The term active galactic nucleus was used as a neutral label, but behind it was a recognition that only a very few physical processes could release so much energy from such a small region. As observations improved, it became clear that many galaxies, including our own, harbor a dark mass at their core, a central object with a gravitational influence so strong that nearby stars whip around it at extraordinary speeds. By measuring those speeds and their distances from the center, astronomers could again infer the mass of the invisible central body. The numbers that emerged were staggering. Even without writing them down here, these central masses were millions or billions of times heavier than the Sun. There was no known way to pack so much mass into such a small region without forming a supermassive black hole. In radio images and X-ray observations, some of these active nuclei show jets, narrow beams of particles and energy streaming out from the vicinity of the central object at almost light speed. That word, almost, hides an important idea in relativity. Light speed is the upper limit for how fast anything, even information, can travel. When we say almost light speed, we mean velocities so high that the usual Newtonian approximations fail, and relativistic effects become crucial. These jets can extend far beyond the visible galaxy, carving structures into the surrounding space. The power required to sustain them is immense. Again, black holes, feeding on infalling matter and converting gravitational energy into radiation and outflows, provide the cleanest explanation. By this stage, black holes had become more than reluctant possibilities. They were central actors in our best models of how galaxies form and evolve. Simulations of cosmic structure that include central black holes produce galaxies that look more like the ones we observe. The very architecture of the universe, on the largest scales we can map, seems to bear the fingerprints of these once hypothetical objects. While all of this was happening on the observational side, the term black hole itself emerged and settled in. Before that, people spoke of collapsed stars or used unwieldy technical phrases. The name black hole is misleading in some ways. These objects are not holes in the sense of gaps or absences, but regions where space-time is intensely curved. Still, the phrase stuck because it captures something important: the absence of light from within, the sense of a place that swallows signals and does not let them out. As the science community gradually accepted black holes as real, the public imagination seized on them in a different way. Stories, films, and illustrations began to feature swirling disks of glowing gas, elongated stars being torn apart, astronauts slipping over horizons. The images were often exaggerated, but the core idea was there. A point of no return embedded in space. A place where familiar rules give way. This interplay between observation and imagination matters. For most people, black holes are not experienced through plots of X-ray intensity or careful fits to stellar orbits. They are encountered as images and metaphors. A black hole as an all-consuming obsession. A black hole as a metaphor for depression. A black hole as the terrifying edge you might fall into if you venture too far. Even scientists are not immune to this symbolic layering. We live with the same language and stories as everyone else. Yet behind the images and myths, the observational evidence keeps pressing in. Telescopes now can do more than infer the presence of black holes. Arrays of radio dishes spread across the globe have combined their data to act like a single Earth-sized instrument, sharp enough to resolve the immediate surroundings of the gigantic black hole at the center of a nearby galaxy. What they see is a dark shadow against a bright ring of emission. A lopsided, glowing halo produced by hot gas circling near the event horizon. This shadow is not the hole itself, but the imprint it leaves on the paths of light around it. That picture does something subtle to our sense of what is real. It is one thing to accept an object because a theory demands it, and because indirect measurements favor it. It is another to look at an image, knowing that it is the accumulated signal of photons that have skimmed past a region where space-time is so warped that not even light on the wrong trajectory can return. The abstract point of no return becomes a dark absence on a screen, framed by the glow of matter that has not yet crossed over. By the time black holes reached this status simultaneously measured, imaged, modeled, and mythologized, they had crossed a cultural event horizon of their own. It became difficult to imagine a universe without them. And once that happened, a deeper question gained traction. If nature is willing to create regions with horizons and hidden interiors, if these objects are not rare accidents but common features woven into galaxies and perhaps necessary for their formation, then perhaps we should take seriously the thought that horizons and interiors might play a role in the universe at the largest scale as well. Not as a plot twist, not as a guarantee, just as a possibility whispered by the same physics that turned mathematical curiosities into shadows we can see. Once you accept that these objects are real and common, another question starts to press in from the edges. If black holes exist all over the universe, what kind of behavior do they bring with them into the story of everything else? The first correction we have to make is almost emotional. Popular images often paint black holes as hungry monsters, roaming space and sucking in anything careless enough to drift too close. The reality is quieter, and in a way more unsettling. A black hole does not chase. It does not hunt. It does not pull harder than any other object of the same mass at the same distance. If our sun were suddenly, and impossibly, replaced by a black hole of exactly the same mass, Earth would continue to follow almost the same orbit. The days would darken, the temperatures would plunge, life would end. But gravitationally, the path would remain. That passivity is important. It reminds us that a black hole is not some additional force in the universe. It is simply gravity pushed to an extreme. The space-time around it is curved in the way any mass curves space-time, just more tightly. The difference is not in what it wants, but in what is possible once you get close enough. Where things become dramatic is in the way matter behaves as it approaches that region of no return. Very little in the universe falls straight in. Clouds of gas and dust, stars, even stray planets carry sideways motion. When they are captured by the gravity of a black hole, that sideways motion becomes orbit, friction, collisions, and magnetic fields in the swirling chaos gradually drain energy from the gas, forcing it to spiral inward. As it does, it forms a flattened structure around the hole. This is the accretion disk. An accretion disk is not a gentle ring. It is more like a cosmic whirlpool of fire. As gas spirals inward, it falls deeper into the gravitational well. Gravitational energy is converted into heat. The gas becomes hotter than the surfaces of ordinary stars. So hot that it shines in ultraviolet light and X-rays instead of mostly visible light. Turbulent magnetic fields thread through the disk, twisting and reconnecting, stirring the flow. The whole structure is a kind of engine, taking in relatively cold interstellar material and spitting out high-energy radiation and, in many cases, powerful outflows. Close to the event horizon, where space-time is most curved, the orbits that matter can follow become precarious. There is an innermost stable orbit, a last circular path where material can loop around without plunging inward. Inside that radius, no circular orbit is stable. Gas that crosses that inner boundary quickly falls onto the black hole. The details of this region depend on whether the hole is spinning and how fast. But the broad picture is similar: a bright, hot disk truncating into a dark interior that cannot send us messages. In some systems, the magnetic and gravitational dance near the black hole does something even stranger. It launches jets. These are narrow beams of particles and energy that shoot out from the region around the black hole's poles at speeds close to the speed of light. The mechanisms that create and collimate these jets are still being worked out. One intuitive way to picture it is to imagine twisted magnetic field lines anchored in the disk and threading the black hole's ergosphere if it is spinning. They act like wires in a cosmic dynamo, extracting rotational energy and flinging matter outward along their paths. Whatever the detailed mechanism, the result is stark. You get streams of matter and radiation that can extend far beyond the host galaxy, boring through intergalactic space, inflating giant lobes of radio-emitting plasma on scales that are almost absurd to think about. These jets do not ignore their surroundings. They push on gas in the galaxy, heating some regions, sweeping others clean, setting up shocks that can either trigger or suppress the formation of new stars. This is one way black holes, which we might first imagine as simple sinks, end up playing a formative role. At the centers of galaxies, supermassive black holes and their accretion disks and jets can regulate how quickly the surrounding gas cools and collapses into stars. If too much gas flows in, the black hole's feeding frenzy ignites bright emission and strong outflows that can blow gas back out, starving the hole and the galaxy's star-forming regions for a time. If too little gas reaches the center, the engine quiets, and the galaxy can slowly accumulate cold clouds again. It is a feedback loop written in gravity and radiation. On much smaller scales, stellar mass black holes in binary systems perform a similar, though more local, role. Their accretion disks flicker and flare, changing brightness as the flow of material from the companion star varies. Sometimes these systems erupt in outbursts when a sudden surge of gas crashes into the inner disk. Observing these changes gives astronomers a way to probe accretion physics in real time, watching as matter spirals through the last few orbits before crossing the horizon. All of this sits in a background where time itself behaves strangely near a black hole. We have already touched on gravitational time dilation. The idea that clocks deeper in a gravitational well tick more slowly relative to those farther out. This is not a trick of perception. It is built into the geometry of spacetime. If you and I start identical clocks together and you stay far away while I descend toward a massive object, then later compare our clocks, mine will have recorded less elapsed time than yours. I will have aged less. Near a black hole, this effect becomes extreme. For a distant observer, processes close to the horizon appear slowed, their signals stretched to longer wavelengths and lower energies. For matter in the disk, following paths that skim near the point of no return, time is simply experienced differently. From its own point of view, the gas heats, orbits, collides, and falls in on a perfectly ordinary schedule. From far away, those events appear smeared, slowed, and dimmed. There is something quietly disturbing about this. We are used to thinking of time as a shared backdrop, something that flows the same way for everyone. Even when we know, in principle, that relativity denies a single universal now, we still live as if there were one. Black holes turn that comfort into a local approximation. Near them, the difference between one observer's story and another's becomes almost impossible to ignore. The same event, gas crossing the horizon, can be both definitively in the past for one participant and never quite completed in the description of another. If we zoom out again and look at the role of black holes in galaxies and clusters of galaxies, another pattern appears. These objects that began as fearful singularities in our imagination turn out to be among the universe's main organizers. The mass of a supermassive black hole at a galaxy's center seems to correlate with properties of the galaxy's bulge, the dense central region of stars. That suggests that the growth of the black hole and the assembly of the galaxy are intertwined. They do not evolve in isolation. They shape each other. In the largest gravitationally bound structures we know of, clusters of galaxies, hot gas fills the space between galaxies and emits X-rays as it cools. Left alone, this gas would condense onto the central galaxies, feeding star formation. But in many clusters, the central black hole injects enough energy through jets and bubbles in the gas to slow this cooling. The result is a kind of cosmic thermostat. Too much cooling and infall, and the black hole flares. We're heating the gas. Too little, and the engine idles. Seen this way, black holes act less like endpoints and more like regulators, nodes in a network of feedback processes that shape structure across cosmic time. They are not isolated abysses, but participants in the universe's tendency to form patterns, galaxies, clusters, filaments stretching across space. This is not the behavior we might have guessed from the phrase black hole. The name suggests only absence and consumption. The reality is more subtle. By letting gravity run its full course, nature creates objects whose presence stabilizes, sculpts, and sometimes violently rearranges their surroundings. The darkness at the center is ringed by emission, outflow, structure. As we think about the possibility that our entire observable universe could be related, somehow, to an interior like this, it matters that black holes are not just final garbage heaps where matter goes to be deleted. In the standard picture, they are deeply involved in processing, redistributing, and encoding information in ways that are still being unpacked. The accretion disk is a furnace and a storyteller, taking in history in the form of gas and stars and sending back a transformed version as light and motion in the surrounding medium. We still do not know, in any complete way, what happens to all the details of the things that fall in. That uncertainty shows up later as the information paradox, the puzzle of whether the fine-grained information about what crossed the horizon is somehow preserved or whether it is lost. For now, it is enough to notice that even at the classical level, without quantum effects, black holes are not simple swallowing mouths. They leave imprints on orbits, on radiation fields, on the very shapes of galaxies. Time runs oddly near them. Matter orbits them in bright, thinning whirlpools. Jets lance out from their vicinities, altering star formation and gas distribution far away. Their masses co-evolve with the systems that host them. In a universe that prefers to build hierarchy from planets to stars to galaxies to clusters, black holes sit at key junctions, gathering and transforming. If we are going to use them as a conceptual mirror for our own cosmos, we need to carry these behaviors with us. The idea that our universe could be associated with a black hole interior is not just a claim about a singularity deep inside. It is a claim, or at least a suggestion, about horizons, disks, flows of information, and the way gravity at its strongest tends to hide what it is doing behind surfaces that we can only see from one side. If horizons are the surfaces that hide what gravity is doing, then singularities are the secrets those surfaces are wrapped around. The places where even the language of physics seems to run out. In everyday life, when we say something breaks, we imagine a physical object snapping, a glass shattering, a bridge collapsing. When physicists say physics breaks down, they mean something quieter and stranger. They mean that the rules we use to describe reality start returning nonsense. Equations stop giving finite answers. Predictions stop being trustworthy. The theory itself raises its hands and says, in effect, I cannot follow you there. A singularity is the name we give to that breakdown inside general relativity. It is not a definite point we can picture, hanging in space like a tiny bead of infinite weight. It is not a speck lurking inside a black hole, waiting to stab anything that comes near. It is a signpost in the mathematics that says, if you follow the natural paths in this space-time, the paths simply end after a finite amount of time or distance. And the theory has nothing more to say beyond that end. Those natural paths have a technical name, geodesics. A geodesic is the path something follows when no forces are pushing or pulling on it except gravity. On Earth, a thrown stone traces an arc in space-time. A freely falling object traces a geodesic. In general relativity, geodesics are the straightest possible lines you can draw through a curved geometry. You do not have to force anything along them. They are the paths that feel like coasting. In a well-behaved space-time, you can extend these paths as far as you like. You can ride them forward, letting your clock tick, without reaching an edge where time simply stops. A singularity, in the precise sense used by the theory, is where this stops being possible. There are geodesics that end after a finite duration, not because your spaceship has hit a wall, but because the mathematical description of space-time cannot be extended any further while keeping the rules of the theory intact. This feature is called geodesic incompleteness. It is tempting to translate that immediately into a picture, everything crushed into zero size, density and curvature going to infinity. The theory often suggests that, in those regions, certain quantities grow without bound. But it is important to understand what infinity means here. It does not tell us what actually exists at that place. It tells us that the way we have chosen to describe reality refuses to give a sensible value. Infinity is not a measurement, it is a flag, inside a black hole. This flag is planted at the very end of every future-directed path that an infalling observer can take. Once you have crossed the event horizon, all time, like directions in space-time, lead eventually to the singularity. Time, like here, means paths along which a physical object with mass can travel. It is the category you and I belong to. In the outside universe, you can choose among many futures. You can decide to go left or right, forward or back. Inside the horizon, the set of possible futures is narrower. No matter what you do, no matter how your rocket fires, your world line bends toward the singularity. This is not like being pulled into a drain in ordinary space. It is more like the direction we call toward the singularity, becoming as unavoidable as the direction we call toward tomorrow. You cannot steer your way into yesterday. You cannot pick a path that never arrives at the next moment. In the same way, once you are inside the horizon, you cannot pick a path that avoids the region where the theory ends. That region lies in your future in a very literal sense. There is a quiet horror in that. Not just because it suggests a destructive end for anything that crosses the horizon, but because it tells us that there are situations in which the best physics we have insists on drawing a blank about what happens next. The equations keep marching forward until, at some finite value of your clock, they simply stop. Now turn your attention to the cosmos at large. When cosmologists take the standard model of an expanding universe and run it backward, shrinking the distances between galaxies, unwinding the stretching of space, They find that the density and temperature grow without bound as they approach a finite time in the past. It is the same kind of signal. Geodesics tracing the history of particles and light rays cannot be extended indefinitely backward. There is a boundary in the mathematical description beyond which the theory ceases to be well defined. That boundary is what we call the Big Bang singularity. Notice the parallel. In a black hole, singularities lie to the future of infalling observers. In the standard cosmological model, the Big Bang singularity lies to the past of every world line we can trace. In both cases, the theory implies that space-time, as it is currently described, is geodesically incomplete. There are histories that simply cannot be continued along the same rules. This is where singularity theorems enter the story. Without diving into proofs, their message is unsettlingly clear. If you assume that gravity always acts attractively on average, that light cones behave in certain reasonable ways, and that trapped surfaces like those inside black holes or in a uniformly collapsing universe form, then general relativity forces you into singularities. You do not get to avoid them by clever coordinate tricks. They are not artifacts of bad notation. They are built into the global structure of the solutions. From one angle, this is a triumph. It means the theory is honest about its own limits. It does not hide its breakdown behind complicated algebra. It tells you, under certain conditions, I will inevitably lead to a place where I fail. From another angle, it is deeply unsatisfying. Singularities are where the questions we most want to ask are located. What really happens at the center of a black hole? What really happened in the earliest moments of the universe? To be told that our main theory of gravity simply cannot answer is like walking to the edge of a cliff in heavy fog. You can feel the drop in front of you. You cannot see the ground below. This is why physicists often say that singularities signal the need for a better theory rather than describing literal physical points. When both general relativity and quantum mechanics become important, as they surely do near these extremes of curvature and density, we expect that a more complete framework, some still unknown quantum theory of gravity, will replace the infinities with finite, describable behavior. Perhaps space-time itself becomes discrete at very small scales. Perhaps the geometry fluctuates in wild but bounded ways. Perhaps the very idea of a sharp point in space or an instant in time dissolves. But notice the pattern again. Whatever that deeper theory looks like, it will have to do more than simply smooth out the math. It will have to explain how, from some finite but extreme regime, a classical world like ours emerges, with stars and galaxies and black holes whose horizons we can see but whose cores we cannot. It will have to tell a story in which the regions that now appear as singularities still play a special role, even if they are no longer places where everything goes to infinity. This is where the idea of a bounce appears in some cosmological models. Instead of a universe beginning from an absolute nothing, the collapse of a previous phase might lead to a minimum size or maximum density, after which expansion begins again. The singularity is replaced by a turnaround, a moment of transition where the old phase gives way to the new. In some pictures, that transition could be quantum in nature, with space-time itself tunneling from one state to another. In others, it might be mediated by additional fields or dimensions. None of these possibilities is settled. All of them are attempts to answer the same discomfort. The feeling that an absolute beginning or an absolute end encoded as a singularity is more a confession of ignorance than a final answer. At the heart of a black hole, similar hopes arise. Maybe the singularity is not a point where everything ends, but a region where our classical ideas break down and new structures appear. There are speculative models in which the interior of a black hole pinches off from the parent spacetime and continues as an expanding region on its own. A baby universe budding off from a parent. There are others where the collapse halts and rebounds, sending information back out in subtle ways. All of these ideas are fragile and incomplete. None has yet earned the authority to replace the raw singularity predicted by unmodified general relativity. So for now, singularities remain as absences in our understanding, sharp edges, places where physics as we know it refuses to go. There is a deeper, almost philosophical unease here. Our theories describe relationships between events, between measurements, between causes and effects. A singularity is a place where that web seems to tear. It is not simply that we do not know what happens. It is that the structure we use to define what happens no longer applies. Questions that seem meaningful outside what is the density, what is the curvature, what is the state, may have no clear translation in a region where the very notions of distance and duration have lost their usual meaning. When we talk about the beginning of the universe in this context, we have to be careful. To say that time begins at the Big Bang is not to say that there was a preceding stretch of empty nothing and then, suddenly, something. It is to say that our current parameter we call cosmic time, the one that works so well to describe the expansion and cooling of the universe after some early epoch, cannot be extrapolated indefinitely backward. The singularity marks the edge of that parameter's usefulness, whether there is a deeper time beyond, whether the universe had a prior phase, whether before is even a meaningful word, are questions the current theory cannot touch. Inside a black hole, the analogous statement is that beyond a certain future, defined by an infalling clock, the description fails. It does not mean nothing exists there. It means that our present understanding of space-time, built around a smooth manifold with a metric field obeying Einstein's equations, is not the right language. This is where singularities, both in black holes and in cosmology, start to feel less like isolated curiosities and more like mirrors held up to our desire for complete stories. We want a narrative that starts at a definite beginning, moves through a continuous middle, and ends somewhere. We want reality to be a book with covers. Singularities tell us that, with our current tools. The pages simply stop, not because the story ends, but because the printing press has run out of ink. The idea that our entire observable universe might live inside the aftermath of a gravitational collapse in some larger reality leans heavily on this parallel. In that picture, what we call the Big Bang singularity would correspond to a region deep inside a black hole from the outside point of view. The end of the story in one domain becomes the beginning of the story in another. The singularity is not a wall but a bridge, not a place where physics fails, but where the description must change. We do not know if that is how things are. But even without committing to any particular scenario, the shared presence of singularities in black hole interiors and in cosmological models forces us to admit that our most successful theory of gravity carries within it a built-in modesty. It works astonishingly well across a huge range of scales and conditions. Yet, when pushed to the extremes we most associate with origin and fate, it tells us plainly, here, I cannot follow. In the gaps left by that sentence, imagination and new mathematics begin to move. Some of that movement will lead to discarded ideas. Some may, eventually, lead to a more complete picture in which singularities are replaced by understandable, if exotic, structures. For our purposes, what matters is not which candidate wins, but the direction of pressure. The breakdowns at singularities are pushing us to reconsider what we mean by beginning, by inside, by cause, and by the universe itself. And as soon as you entertain the possibility that the edges of our equations might hide connections to other regions, other phases, other layers of reality, it becomes natural, perhaps unavoidable, to ask whether the very dimensionality of the world we experience is the whole story, or whether our familiar three-dimensional space is just a slice of something larger. The thought that our own space-time might be just a thin slice of something larger is hard to hold still. It keeps unfolding. Like a page that wants to reveal the rest of the book it was torn from. We move through the world as if its structure were obvious. Left and right. Forward and back. Up and down. 3 spatial directions. Plus the one we call time. We do not count them consciously, but our language and movements always assume them. When you reach out to touch a glass of water, when you walk down a street, when you look up at the sky, you are navigating that 3 plus 1-dimensional stage. For a long time, that seemed like the whole story. Space is the 3-dimensional arena. Time is the 1-dimensional river. Physics describes how things move and interact within that 4-dimensional blend. Why ask for more? Extra dimensions begin not as a wild guess, but as a response to a problem. How do we unify the different forces of nature under a single framework? How do we make gravity and quantum mechanics, which are both astonishingly successful in their own realms, speak the same language without contradiction? One of the earliest suggestions that more dimensions might help came from trying to combine gravity with electromagnetism, the force that governs light and charged particles. The idea was simple to state and deep in its implications. What if, instead of living in a 4-dimensional space-time, the universe had an extra hidden direction? Not a direction we can walk along, but one that is curled up so tightly that we do not notice it. To picture this, imagine an ant crawling along a thin wire stretched across a room. From far away, the wire looks like a 1-dimensional line. The ant seems to have only 2 options, forward or backward. But if you come close, you see that the wire has thickness. The ant can also move around the circumference. What looked like 1 dimension from a distance is actually 2. 1 long, 1 tightly wrapped. In these early models, our familiar space-time is like the long direction of the wire, and the extra dimension is like the wrapped one. Fields that represent forces can spread out in all available dimensions. Certain patterns of how they wrap around the extra dimension show up, from our lower dimensional perspective, as distinct forces or particles. The hope was that by allowing space-time to have an extra direction, gravity and electromagnetism might be understood as different aspects of a single higher dimensional field. These first attempts ran into difficulties, but the seed was planted. Extra dimensions were no longer pure fantasy. They were a tool you could try to use, a space in which equations might line up more neatly. Much later, string theory took this idea and sharpened it into something more demanding. In string theory, the basic building blocks of matter and forces are not point particles, but tiny 1-dimensional strings. These strings can vibrate in different patterns, and each pattern corresponds to a different particle, an electron, a photon, a graviton, and so on. For the mathematics of string theory to be consistent, however, space-time cannot be just 4-dimensional. The theory insists on more. In its simplest versions, string theory requires a space-time with 10 dimensions, 9 of space, 1 of time. In related frameworks that try to unify different string theories, there can be 11 dimensions. We do not see 9 extended spatial dimensions in everyday life, so the extra ones must be hidden in some way. The usual approach is to imagine that only 3 of the spatial dimensions are large and extended, while the others are compactified, curled up into shapes so tiny that we cannot probe them with any current experiment. The shapes used for this compactification are not simple circles like the wire's circumference. They can be intricate, multi-dimensional objects with a rich internal geometry. The way they are folded determines the kinds of particles and forces that exist in the lower dimensional world we perceive. If you change the shape, you change the physics. It is as if the unseen, microscopic structure of space itself writes the menu of possible realities. This is an alluring picture, but also a fragile one. There are many ways to curl up extra dimensions, and it is not yet clear which, if any, corresponds to our universe. What matters for our story is not the catalogue of possible shapes, but the underlying move, accept that what we call the universe may be just the visible part of a higher dimensional object. From here, another idea emerges. One that moves the focus from tiny curled dimensions to large hidden ones. Brain cosmology begins with a simple shift in emphasis. Instead of thinking of the extra dimensions as compact and microscopic, it imagines that at least some of them might be large or even infinite in extent. While our familiar three-dimensional space is a kind of membrane, shortened to brain, floating inside that higher dimensional space, often called the bulk. A brain is a generalization of the idea of a surface. A two-dimensional surface like a sheet of paper can live inside a three-dimensional room. Similarly, a three-dimensional brain can live inside a higher dimensional bulk. Everything we know, matter, light, the forces that act between particles, could be confined to this brain, unable to move off it into the extra dimensions. Only gravity, in some models, is allowed to leak into the bulk. This leakage offers an intriguing clue about one of the long-standing puzzles of physics: why gravity is so much weaker than the other forces. You can feel the electromagnetic force when you rub a balloon on your hair and make it stick to a wall. That small charge is enough to overcome the gravitational pull of an entire planet on the balloon. If gravity is the fundamental architect of cosmic structure, why is it so feeble at human scales? In brain models, one possible answer is that gravity is not truly weak. It only seems weak because its field lines can spread out into the extra dimensions, diluting their intensity on our brain. Think again of the wire and the ant. If sound could propagate only along the wire, but light could spread into the whole room, then at a distance, the sound would seem much weaker, simply because it has fewer directions to travel. In a brain world, the opposite happens. The forces confined to the brain are concentrated, while gravity spreads out into the bulk. This is not just a poetic metaphor. There are specific higher dimensional models in which the equations of gravity, when projected onto the brain, reproduce something very close to Einstein's general relativity, with small corrections at very short or very long distances. These corrections might, in principle, be detectable in experiments that measure gravity at tiny scales or in precise observations of cosmic expansion. So far, the evidence is not decisive. The data constrain these models, but do not completely rule them out. The picture that emerges is striking. Our universe might be like a three-dimensional island embedded in a sea of higher dimensional space. All the particles and fields we can manipulate are waves on the surface of this island. We build colliders, point telescopes, and perform measurements. But we are always probing the physics of the brain. The bulk remains indirectly sensed, inferred through the way gravity behaves. Now bring black holes back into this setting. In a higher dimensional world, black holes can have richer structures than in simple four-dimensional general relativity. Their horizons can wrap around brains, pinch off into the bulk, or extend along extra dimensions in string-like or membrane-like shapes. A familiar Schwarzschild black hole is no longer the only possible configuration. There can be black brains, extended objects with horizons that stretch across some dimensions while remaining localized in others. If our observable universe is a brain, then a black hole, from our perspective, might actually be the intersection of a higher dimensional black object with our three-dimensional world. Like slicing through a loaf of bread, we would see only a cross-section of the full geometry. The event horizon we infer could be the shadow of a more complex horizon structure in the bulk. In some speculative scenarios, the formation of a black hole in the bulk could have consequences that look, on the brain, like a cosmological event. A collapsing region in the higher dimensional space might, when viewed from within the brain, resemble a Big Bang, an expanding region of hot, dense matter emerging from what appears to be an initial singularity. From the bulk's point of view, this expansion is just the internal dynamics of a black hole or related object. From the brain's point of view, It is the birth of a universe. These ideas are delicate. It is easy to push them into science fiction. But at their core is a simple conceptual shift. Rather than thinking of the universe as the totality of everything that exists, we think of it as the totality of what can be accessed along the degrees of freedom available to us, which may be confined to a lower dimensional slice. An interior can exist, in this view, not only inside a horizon but also inside a brain. The notion of a bulk also reframes what outside means. When we ask whether there is an outside to the universe, we often imagine a larger empty space surrounding it, like a void around a bubble. In a brain world, the bulk is not an empty container. It is a dynamic, higher dimensional space-time with its own fields and perhaps its own objects, of which our universe is a substructure. Outside is not a place you can travel to with a rocket. It is a set of dimensions you cannot access because the physics that governs you is confined. This confinement is not prison-like. It is simply the way the laws of nature are written. Photons, the particles of light, for example, might be excitations of fields whose vibrations are bound to the brain. They have no degree of freedom that points into the bulk. They cannot leave the island. Gravity, encoded in the curvature of the bulk itself, is not so limited. It touches both brain and bulk freely. From the perspective of someone living entirely on the brain, the bulk is an inferred reality. You cannot point and say, "There it is." You can only notice patterns that are hard to explain without allowing for those unseen dimensions. Gravity's weakness. Certain possible signatures in high-energy collisions. Specific imprints in cosmic evolution. The bulk is like the interior of a black hole in that sense. Its presence is known through its effects, not through direct inspection. For our main question, could our universe be the interior of a black hole? The language of brains and bulk gives us another way to think about inside and outside. A black hole in the bulk could have an interior that, from its own point of view, includes a brain that inflates and cools in a way that looks like our cosmos. The singularity that appears at the heart of the black hole in lower dimensional descriptions might correspond, in the full higher dimensional geometry, to a transition surface where a brain is created or pinches off. Again, none of this is settled fact. These are frameworks in which such pictures have been worked out in mathematical detail, but they are not yet anchored by decisive observational evidence. Their role here is not to ask you to believe them, but to show that physics already entertains serious models in which what we call the universe is not the absolute totality. It is a part of a bigger structure, a sheet in a stack, a slice in a loaf. There is a quieter consequence of thinking this way. If we live on a brain in a bulk, then even the most ambitious cosmological survey, the deepest sky map, the most careful measurement of background radiation, the longest observation of distant galaxies is still an internal census. We are measuring the properties of our own sheet. We do not know how many other brains might exist, parallel or intersecting. We do not know how the bulk is arranged on scales beyond our causal reach. Our entire field of view, in spatial and temporal terms, could be a local patch in a space that is, in a very literal sense, higher. This does not make our observations meaningless. It makes their limitations more explicit. In a higher dimensional picture, the phrase observable universe is almost redundant. Of course, we see only the observable part. But what counts as universe becomes a matter of which layer you are talking about. The brain, the bulk, the whole structure that contains both. If horizons taught us to question the idea of a single all-seeing vantage point within space-time, extra dimensions and brains teach us to question the assumption that space-time itself is the full stage. They suggest that our most basic intuitions about dimension, about inside and outside, about what it means for something to be the whole of reality, are shaped by our confinement to a particular slice. When you hold that in mind, and then look back at black holes, they begin to feel different. A black hole is no longer just a pit in space. It is a region where the rules that separate interior from exterior are enforced by geometry. In a higher dimensional context, those regions can connect, branch, and give rise to lower dimensional structures. A brain like ours could be, in some models, the product of such a process. We do not need to commit to this picture to feel the pressure it exerts on our language. Saying, "The universe began with the Big Bang," assumes that the brain is the whole, that cosmic time is the only relevant time, that our dimensions are all the dimensions. The moment you allow higher realities, that sentence becomes more modest. It turns into "our brain," with its particular fields and particles, entered a hot, dense, expanding phase. It no longer claims to describe the totality of whatever exists in the bulk. The possibility that our universe could be inside a black hole in a higher dimensional space fits naturally into this layered view. It is not a claim that can be checked by looking for a physical wall at the edge of the observable universe. It is a suggestion that the patterns we see, singularities, horizons, expansion, the behavior of gravity, might be shadows of a larger structure in which inside and outside are relative to which level of the hierarchy you inhabit. In that sense, extra dimensions and brains do not so much answer the question of where our universe sits as dissolve the assumption that the question has a single, simple answer. They turn the word universe from an absolute into a label for a layer. And once you start calling it a layer, it becomes easier to imagine that what feels like everything may itself be the interior of something else. If our universe might be a layer inside a larger structure, a quieter question starts to glow at the edges of that idea. What if even that layer is not as solid as it seems, but a kind of projection of something stored on its boundaries? The path to that thought does not begin with philosophy. It begins with bookkeeping. Physicists, in their more honest moments, are often just arguing about how to count. How many ways can the atoms in a gas be arranged while still looking macroscopically like the same gas? How many microscopic configurations correspond to the same cup of coffee, the same star, the same chunk of metal? This is what entropy measures at a deep level, not disorder in the everyday sense, but the number of microscopic possibilities consistent with the same large-scale appearance. In ordinary situations, there is an intuitive expectation about how this counting should work. If you double the volume of a box of gas while keeping the density the same, you have doubled the number of atoms. Roughly speaking, you have more room for more configurations. So the entropy should grow with the volume. The bigger the region, the more ways the stuff inside it can be arranged. Area, the size of the surface, feels like the wrong quantity to pay attention to. The physics of a room, you might think, is about its interior, not about its walls. Black holes quietly reverse that expectation. When people began to take black hole thermodynamics seriously, they noticed something odd. You can assign a temperature to a black hole and an entropy as well, as if it were a physical system with microscopic degrees of freedom we do not yet understand. But the entropy of a black hole, the measure of how many internal states it could have, does not scale with the volume enclosed by the horizon. It scales with the area of the horizon itself. This is a sharp statement. Take a black hole and imagine, in principle, increasing its mass so that its event horizon grows. The maximum amount of information that can be hidden behind that horizon increases in proportion to the area of the horizon, not the volume inside. Add more mass. Get a larger horizon. Acquire more entropy. The rule follows the surface, not the interior. It is hard to overstate how strange this is when you first encounter it. In everyday intuition, if you want to cram more information into a region, you use more of its inside. You fill the shelves, then the air between them, then every spare corner. With black holes, Nature seems to say, the ultimate storage capacity of a region is written on its boundary. The limit is an area law. The interior behaves as if its information content is already accounted for on the surface. From this simple but radical observation, a new principle slowly emerged. If the maximum entropy inside any region is proportional to the area of its boundary, perhaps the deepest description of that region's physics lives on that boundary as well. Perhaps the volume is, in some sense, a way of organizing information that is fundamentally stored on a lower dimensional surface. This is the holographic principle. The name borrows from a familiar piece of technology. A hologram, in the everyday sense, is a two-dimensional pattern on a surface that, when illuminated in the right way, produces the appearance of a three-dimensional object. The thickness of the plastic or glass that holds the pattern is irrelevant. The depth you see is encoded in the interference of light and dark on the surface. The three-dimensional scene is not inside the slab. It is in the information etched into it. The holographic principle suggests something more radical than that simple analogy. But the flavor is similar. It says, under certain conditions, the physics in a region of space with gravity can be exactly equivalent to a theory without gravity living on a boundary of that region. In one fewer spatial dimension, everything that happens in the bulk, the interior, has a precise counterpart on the boundary. Every particle, every field, every interaction in the higher dimensional picture can be translated into some configuration in the lower dimensional one. If that sounds like a wild conjecture, it is worth noting that in at least one carefully defined context, something like this has been shown to work with astonishing detail. A particular kind of spacetime with negative curvature, often called anti-de Sitter space, turns out to have a dual description as a quantum field theory living on its boundary. This relationship is sometimes called a correspondence, and while its name is technical, the core idea is simple enough. There is no deeper, more fundamental description that sits above both sides. The bulk gravity theory and the boundary non-gravitational theory are just two languages for the same underlying physics. Imagine a book written in two different scripts. One version is in a language that naturally describes smooth curves of spacetime, horizons, and gravitational waves. The other is in a language that naturally describes particles, fields, and quantum interactions on a fixed background. There is a dictionary between them. A question asked in one language can be translated sometimes into a simpler question. On the other side, the story is the same. The ways of telling it are different. In this duality, black holes in the bulk correspond to states of the field theory on the boundary with high entropy and temperature. The horizon area in the higher dimensional picture maps to the entropy of the lower dimensional system. The evaporation of a black hole under quantum effects has a translation into ordinary thermal processes on the boundary. The interior of the black hole, which seems so hidden from the bulk perspective, is in some sense fully encoded in the boundary data. This is not metaphor. It is a literal equivalence between two complete theories. Work out the behavior of one, and you have in principle worked out the behavior of the other. Even if you never explicitly do the translation, for many physicists, this was the first convincing demonstration that the holographic principle is more than a suggestive slogan. It is a concrete realization of the idea that a gravitational theory in a volume can be completely captured by a non-gravitational theory on a lower dimensional boundary. What does this have to do with our question about whether the universe could be inside a black hole? It adds a new layer of discomfort to the notion of interior and exterior. In the holographic view, the information about what happens inside a region can be fully captured on the boundary. The inside is not being ignored, it is being redescribed. An observer who has access only to the boundary theory can, in principle, reconstruct everything that would be seen in the bulk. The interior is emergent, a way of packaging correlations in the boundary degrees of freedom. If you combine that with the earlier idea that our universe itself might be a brain in a higher dimensional bulk, You get a chain of possibilities. A higher dimensional black hole could have an interior that includes a brain like ours, whose physics, in turn, might have a holographic dual description on some higher dimensional boundary we cannot access directly. The hierarchy of inside and outside becomes a network of representations rather than a simple nesting of spaces. At this point, it is easy to drift into the language of illusion, to say that the bulk is not real, that only the boundary is fundamental, or to flip it and say that the boundary is only a convenient encoding of a more visceral interior reality. The holographic principle itself does not choose sides. It simply states that for certain systems, both descriptions are equally valid and complete. The question of which is more real may be more about our preferences than about physics. There is, however, a clear pressure on our intuitions. We like to imagine that there is a one-to-one correspondence between spatial extent and physical content. A larger room holds more things, in a literally volumetric way. Holography suggests that, at least near strong gravitational regimes, the amount of information needed to describe a region does not care about how much interior volume you draw on your map. It cares about the area of the boundary. The interior is economical. It does not demand its own independent count of bits. This way of thinking has consequences even when we step back from exotic spacetimes and look at our own cosmic horizon. Our observable universe is surrounded not by a physical wall, but by a light-like boundary defined by how far signals could have traveled since the earliest times. Some researchers have asked whether a holographic description could apply here as well, whether the degrees of freedom needed to encode everything we can ever observe might be counted on that cosmic boundary in some generalized way. The technical details are subtle and far from settled, but the conceptual move is simple. Instead of thinking of the universe as an expanding ball of stuff in a pre-existing void, you think of it as a region whose observable content is constrained by an area law tied to its horizon. The deeper you push that thought, the less comfortable it becomes to talk about an absolute interior at all. What you can meaningfully label as inside depends on which horizon and which boundary your description uses. A striking point in all of this is that holography does not say that the world is fake, or that we live in a computer simulation run elsewhere. Those are separate ideas, often layered on top in popular discussions. The holographic principle is quieter. It says that there may be multiple equivalent ways to describe the same physical reality, some of which use fewer spatial dimensions than others. It is about representational redundancy, not about deception. If our universe, or some sector of it, has a holographic dual, then what we experience as three-dimensional space and one-dimensional time could be an emergent way of organizing information whose most compact description lives on a lower dimensional structure. That does not make the chair you are sitting in less solid. It does not make your memories less yours. It does suggest that solidity and continuity may be properties of a particular description rather than of some ultimate layer. For the black hole interior idea, holography adds both support and ambiguity. On one hand, it shows that information swallowed by a horizon does not have to be lost in any absolute sense. It can be preserved in subtle correlations on the surface, in line with the demands of quantum mechanics. On the other hand, it blurs the meaning of interior itself. If everything that happens inside can be fully represented on the boundary, then calling our universe the inside of a black hole in some higher reality becomes less a claim about location and more a claim about which representation we inhabit. There is also a more personal unease that comes from sitting with these ideas. We are used to thinking of ourselves as beings inside a space, looking out at objects that are also inside that space. We imagine an almost godlike, imaginary viewpoint outside the universe, from which the whole thing could be seen at once. Holography quietly undermines that imagined view, not by forbidding it, but by making it irrelevant. There is no privileged vantage point from which the universe is finally and truly seen as it is, independent of description. there are only mutually consistent descriptions, each with its own natural language and its own blind spots. If reality can be equivalently described as a gravitational bulk or as a lower dimensional field theory, if a black hole's interior and its horizon data are two faces of the same coin, then our insistence on a single biless, intuitive picture of what is really happening starts to look like a preference conditioned by evolution and experience, not a property of the universe. This brings us back to the theme running quietly underneath our original question. When we ask whether the universe could be inside a black hole, we are not only asking about geometry, we are asking about where we imagine ourselves to be standing when we make that statement. Inside relative to what? On which descriptions map? In which number of dimensions? The holographic principle does not answer those questions. It does something more uncomfortable. It suggests that the map and the territory may be less distinct than we hoped. That what we call inside a region of spacetime might, from another angle, be nothing more or less than the way a boundary encodes its information. That our notion of a universe as a big room containing everything is a useful but parochial metaphor. Black holes first taught us that information might be stored on horizons. Holography teaches us that, in some cases, that storage is not a mere accounting trick, but a complete description. Extra dimensions and branes remind us that the horizon itself might be only a layer in a higher dimensional structure. Together, these ideas form a kind of conceptual pressure chamber. They compress our everyday picture of reality until something gives, the belief that there is a single, natural, volumetric universe that simply is, with us safely inside it. Looking out, what we are left with instead is a layered, relational view, regions defined by horizons, descriptions defined by boundaries, interiors that may be emergent, a universe that could, without contradiction, be both an interior in one sense and a projection in another, and somewhere inside that stack of equivalences, small beings drawing diagrams in four-dimensional space-time, trying to decide which of their images, if any, deserves to be called the whole. If reality can be told as a story on a boundary, the next unsettling question is simple. What happens to that story when the boundary itself slowly glows and disappears? Black holes were named for their darkness, but the deeper trouble began when they refused to stay completely black. The classical picture is straightforward enough. Matter falls in, the horizon expands, the singularity waits at the core. Whatever crosses the boundary never returns, at least not as anything we can see. Information, in the everyday sense, seems to go one way. Quantum theory does not like one-way doors. In the quantum view, emptiness is never really empty. Even the vacuum, the state we would naively call nothing, is alive with restless possibility. Fields that fill all of space are constantly jittering. They fluctuate. At very small scales and very short times, they can momentarily borrow energy, create pairs of particles and antiparticles, and then annihilate again, paying the energy back. These fleeting excitations are sometimes called virtual particles, not because they are fake, but because they cannot be directly plucked out and bottled. They are internal ingredients of the quantum world. When you bring a horizon into that restless vacuum, something subtle happens. Near the event horizon of a black hole, these fluctuations feel the extreme curvature of space-time. The intuitive story, the one often told in popular accounts, goes like this. A pair of virtual particles appears just outside the horizon. Normally, they would meet again and annihilate, leaving no trace. But if the horizon lies between them at the moment of their birth, one can fall in while the other escapes. To an observer far away, the escaping particle looks like radiation emitted by the black hole. The infalling partner carries negative energy relative to the outside, reducing the mass of the whole. This picture is not literally how the detailed mathematics works, but it is a useful image. The key point is that When quantum fields are placed in the curved spacetime around a black hole, the result is that the hole emits radiation with a spectrum that looks thermal, like the glow from a hot object. The temperature is extremely low for large black holes, much colder than the background of the universe today, which is why this radiation is essentially impossible to detect from astrophysical holes. But in principle, if you wait long enough, the black hole will radiate away its mass. It will evaporate. That realization changed the status of black holes in a profound way. They were no longer eternal prisons. They were temporary configurations that could, given enough time, disappear. The horizon would shrink. The singularity, if it exists in the classical sense, would eventually be exposed to whatever the true quantum theory of gravity does in those extreme conditions. The end state, in the simplest picture, would be just a bath of featureless radiation. Here the bookkeeping re-enters, and with it, the paradox. In quantum mechanics, information is not just a casual word. It has a technical flavor. A pure state, a perfectly specific quantum condition, evolves in time according to rules that are reversible. If you know the state exactly at one moment, and you know the governing dynamics, you can, in principle, reconstruct its past and calculate its future. The evolution is unitary, which means no information about the exact state is ever truly destroyed. It can be scrambled, dispersed, hidden in correlations between widely separated pieces of the system, but it cannot simply vanish. Now, imagine a star in a pure quantum state. It collapses under gravity and forms a black hole. The black hole then evaporates completely, leaving behind only thermal radiation. Thermal radiation, at first glance, carries only coarse-grained information: its overall temperature, its total energy, its broad spectrum. It looks the same no matter what specific details went into the formation of the black hole. A star with a certain mass and chemical composition, or a cloud of gas formed in a different way, would produce the same simple thermal output once it became a black hole. If that were the whole story, information would be gone. The many microscopic details that distinguished one initial state from another would have been swallowed by the singularity and then erased when the black hole vanished. The outgoing radiation would not carry a faithful record. You could not, even in principle, reconstruct what fell in from what came out. That would be a violation of unitarity, a break in the core logic of quantum mechanics. This conflict is what people mean by the black hole information paradox. It is not about everyday secrets crossing the horizon. It is about the consistency of physical law. One of our best theories of gravity says that horizons can hide and then erase details. One of our best theories of the microscopic world says that complete erasure is forbidden. They cannot both be universally right in their current form. There are, broadly speaking, a few ways to respond, each with its own cost. One is to accept that quantum mechanics might need to be modified, perhaps in the presence of horizons and singularities. Evolution is not strictly unitary. Information can be genuinely lost. The universe is not, at the deepest level, reversible. That path feels radical, because quantum theory has been tested in countless ways with extraordinary success. Changing its core structure would ripple through all of physics. Another is to insist that information is not lost, but is somehow locked into a remnant, a tiny final object left behind after the black hole has radiated most of its mass away. This remnant would have to be able to store an enormous amount of information in a minuscule package. That idea runs into its own difficulties, both conceptual and technical. It risks introducing a zoo of highly degenerate states that can be produced in many ways, which can create more problems than it solves. A third, and now widely explored, possibility is that Hawking radiation is not perfectly thermal after all. It may look thermal when you look only at simple averages, but at a finer level, there could be delicate correlations between different quanta of radiation. Correlations that encode the information about what fell in. The radiation would then be like a long, subtle code. Each particle by itself tells you almost nothing. The pattern, woven by the entire sequence, preserves the initial state in a highly scrambled form. From this viewpoint, evaporation would be unitary. The paradox dissolves, but only if those correlations truly exist. The difficulty is that Hawking's original calculation, which treats the space-time geometry classically and the fields quantum mechanically, does not show such correlations. It gives you a neat, thermal spectrum. To find the finer structure, you need a more complete theory that treats both geometry and fields quantum mechanically. That is where holography re-enters. In holographic models, a black hole in the bulk corresponds to a state in a quantum field theory on the boundary. The boundary theory is manifestly unitary. Its evolution preserves information. If the bulk and boundary descriptions are truly equivalent, then the process of black hole formation and evaporation in the bulk must also be unitary. Even if the bulk calculation is hard to perform in practice, this has led many to believe that, in a correct theory of quantum gravity, black holes do not erase information after all. They only hide it temporarily. But if the information comes out, where was it stored? And how does its release look to different observers? Here, another idea, sometimes called black hole complementarity, enters. The suggestion is that we may not need a single description that works for every observer at once. For someone remaining far away, watching the hole evaporate, all the information about what fell in might be stored on or near the horizon, then slowly emitted in the radiation. The infalling matter never truly crosses the horizon in that observer's description. It becomes part of a stretched, hot membrane just outside. For an observer, falling in. By contrast, nothing dramatic happens at the horizon. They pass through, experiencing smooth space-time, and carry their information with them toward the interior. The two stories contradict each other if you try to blend them into a single global picture. But if no observer can compare notes from both regions inside and outside the horizon, maybe the contradiction is harmless. Each description is self-consistent within its own domain. No single experiment can reveal the duplication. Information is both on the horizon and inside, but never in a way that allows a violation of fundamental quantum limits. This sounded, for a time, like a promising compromise. Gravity keeps the horizon gentle for infalling observers. Quantum mechanics keeps information from being destroyed for distant observers. The inability to unify both perspectives into a single global frame is a price some were willing to pay. Then the logic was pushed further, and another unsettling possibility emerged. If you combine the demands of unitarity with the assumption that an infalling observer should experience nothing special at the horizon and with some basic facts about quantum entanglement, you run into a conflict. Entanglement is a kind of deep correlation between quantum systems, one that cannot be explained by shared classical information. In Hawking's picture, each outgoing quantum of radiation is entangled with a partner that falls in. As evaporation proceeds, the early radiation can also become entangled with later radiation if information is to come out. But there is a limit to how entangled a system can be with different partners at once. Quantum correlations are monogamous in a precise way. The argument, in rough form, goes like this. Near the end of evaporation, the late radiation cannot be fully entangled both with the interior and with the early radiation. Something has to give. Either the horizon is no longer a smooth place for infalling observers, there is a violent firewall of high-energy excitations waiting there, or information is not fully carried out in the radiation, or quantum mechanics needs revision. Each option claws at a different pillar. This so-called firewall paradox is still a matter of active debate. Different proposals try to evade it in different ways. Some suggest that the interior of a black hole is not an independent region at all, but is fully encoded in the outgoing radiation in a way that makes talk of a separate inside redundant. Others explore more radical changes to the way space-time emerges from entanglement. None of these ideas is settled. What matters for us is the pattern. Every attempt to rescue both the interior and unitarity forces us to think of space, time, and information in less naive ways. In all of this, the word information risks feeling abstract and bloodless. It can help to ground it. Imagine a book with a particular sequence of letters. Burn the book. In a classical world, the information about that sequence is not strictly lost. It is dispersed into the smoke, the ash, the outgoing radiation. In practice, it is gone for you. In principle, a Laplacian demon with access to all the microscopic details could reconstruct it. In a quantum world, the demand is harsher. The evolution from book to smoke must be described by a unitary transformation. No amplitude in the full wave function is erased. The pattern is scrambled, but still present. The black hole information paradox is that burning a book is like tossing it into a fire you can, in principle, watch from outside. Tossing it into a black hole that later evaporates is like watching the fire from behind a wall that permanently hides the hottest flames. If, when the wall is gone, the remaining ash and smoke are completely generic, independent of what you threw in, then some part of the pattern is truly missing. The microscopic details have no place to hide. If our universe were in any way analogous to such an interior, this question scales up. When we talk about the Big Bang, about the apparent singularity in our past, we are not only asking what physical processes occurred, we are asking what happened to the information about any prior state. If such a prior state existed, was it encoded somehow in the pattern of fluctuations we see in the cosmic background? Was it erased by some quantum gravitational process? Are we, like an outside observer watching a black hole evaporate, destined to see only a coarse thermal output from a history we can never fully reconstruct? Holography, again, suggests a more optimistic answer. That information is never truly lost, only translated. But it is an optimism that comes with a cost. It requires us to accept that the interior we imagine, whether the interior of a black hole or the interior of the observable universe, might be a derived concept, useful within a certain regime, but not fundamental. The fundamental bookkeeping happens elsewhere, on boundaries we cannot directly touch. For our sense of being beings inside a world, this is a strange position to inhabit. We live by local stories. A person walks into a room, says a sentence, leaves, an object falls into a box, stays there. We rely on the idea that somewhere, in principle, a complete account exists that tracks every detail of these stories. The information paradox says, if horizons and evaporation are real, your instinct about where that complete account lives may be wrong. In the black hole case, the tension is explicit. Either you give up on strict quantum unitarity, or you give up on a naive picture of the interior, or you accept that space-time and entanglement conspire in ways that are deeply counterintuitive, perhaps making the inside of the hole and the pattern of its radiation two ways of describing the same underlying degrees of freedom. In the cosmological case, the tension is quieter, but similar. We are surrounded by horizons, limited by the finite speed of light and the finite age of the universe. If some version of holography applies, the full account of our observable region might be stored on a surface that, from our viewpoint, lies infinitely far away in space or in time. The information about our past and future might not be inside in any simple geometric sense, standing here, somewhere between these layers of theory and image. The original question, could our universe be inside a black hole, starts to shift tone. It becomes less a concrete claim about a particular object and more a pointer to the deeper unease. If even black holes may not have interiors in the straightforward way we imagine, if their insides can be re-expressed as patterns on a surface, then the very notion of being inside anything cosmic becomes suspect. And yet we continue to fall. In the conceptual sense, we use these paradoxes not to find a comforting resolution, but to strip away assumptions that horizons are places we could, in principle, cross and then look back from. That information has a single, obvious home, that the universe's story can be told from a vantage point that does not itself sit somewhere in the web of cause and effect. In the tension between gravity's horizons and quantum theory's insistence on unbroken information, we are pushed toward a view of reality in which inside and outside are not fixed categories. They are roles played by different descriptions, and once that becomes clear, another question waits at the edge of thought. If crossing a black hole's horizon means entering a region whose fate is entangled with an outside you can never access again, what does it mean that we ourselves live within a cosmic horizon that we can never escape? It is a strange thing to realize that we may already be living inside a horizon, watching light struggle to reach us from the edges, and still have no real intuition for what it means to cross one. So let us imagine it, slowly and carefully, not as a cartoon plunge into darkness, but as a sequence of frames in which the rules we rely on begin to tilt. You are far from the black hole at first. Out here, space-time is only gently curved. Stars still follow familiar orbits. Light from distant galaxies travels almost in straight lines. Clocks tick in ways that, although relativity says they are not truly universal, feel close enough to a shared rhythm that we treat them as such. The black hole is just another massive object, darker than most, influencing motions around it in ways that can be calculated with unremarkable precision. As you fall inward, guided only by gravity, there is nothing like an invisible wall pulling you. You simply follow a geodesic, that natural path through space-time that feels like coasting. If you cut your engines, stop firing rockets, and surrender, that path is what you trace. In your own frame, you are weightless. You feel no pull because you and your spaceship are both being curved along together. Still, there is a difference you cannot ignore for long. The black hole grows larger in your forward view. Stars behind you appear increasingly smeared and blue-shifted in a narrow patch of sky. As light from them is bent and focused by space-time curvature, the rest of the cosmos slides toward a ring around the hole, distorted by gravitational lensing. It is as if the universe is rearranging itself on your horizon of vision, concentrating into a bright, warped halo. If you look back toward some distant friend hovering far away, you discover that light signals take longer and longer to reach them. Their replies arrive increasingly delayed. Your clock and theirs begin to part ways. To you, your heart beats steadily. Your thoughts unfold at their ordinary pace. To your distant companion, your signals slow, their timestamps stretched, their frequencies sliding toward the red. Your voice seems to drag. This asymmetry is one of the key features of approaching an event horizon. For the distant observer, you never quite cross it. You appear to freeze just outside, dimming gradually as your light is stretched to longer wavelengths. For you, nothing of the sort happens. There is no pause, no sense of hanging at the edge. You pass through the critical surface in a finite time on your own clock, continuing inward without encountering a physical barrier. An event horizon is a boundary in what can influence what. It is drawn not on space, but on space-time, separating events that can send signals to the outside from events that never will. It is defined by the global structure of light cone, those little diagrams that show the future directions in which light can travel from a given point. Outside the horizon, Some of those future directions reach distant observers eventually. On the horizon, the outward-pointing directions skim along the boundary. Inside, every future direction bends inward. No choice of motion can change that. Before you cross, you might try something reckless and hopeful. Fire your rocket. Aim outward. Try to escape. If you are still above a certain altitude, above the surface defined by the Schwarzschild radius, there is a path that leads back out, though it may cost more fuel than you have. If you cross that altitude, no thrust is enough. Even a photon, the fastest possible messenger, cannot be launched on a trajectory that reaches infinity. It can only spiral inward, buying perhaps a little extra proper time before reaching the singularity, but never avoiding it. From your viewpoint, though, nothing dramatic marks that moment. The radial coordinate that outside observers use to describe your position is losing its direct spatial meaning. Inside the horizon, what was once a radius you could treat as a distance becomes more like a time coordinate, something that must increase along any future directed path. Moving inward is no longer a choice of direction. It is as inevitable as moving from past to future. Meanwhile, space around you narrows in another sense. The directions perpendicular to your fall remain space-like. You could, in principle, move sideways, circle the center, turn a little left or right, but none of these maneuvers changes the fact that the value of the radial coordinate will tick downward, step by step, toward the singularity. The geometry has resorted what counts as space and what counts as time. The tidal forces, the differences in gravitational pull between your head and your feet, between one side of your ship and the other, also begin to show themselves. Far from the black hole, they are negligible. Near the horizon of a truly supermassive black hole, they might still be gentle, weak enough that you would not notice them as you cross. For a smaller black hole, the gradient becomes fierce sooner. Your body is stretched along the direction of fall and squeezed in the perpendicular directions in a process that has picked up the morbid name spaghettification. It is not a poetic flourish. It is a straightforward prediction of differential gravity. In a realistic astrophysical hole, rotation complicates the picture further. Spinning black holes drag spacetime around with them, a phenomenon called frame dragging, in the region outside the horizon but close to the rotating mass. This effect becomes so strong that nothing can remain static relative to the distant stars. Everything is forced to co-rotate to some degree. This region is called the ergosphere. Inside it, energy can be extracted from the rotation of the hole in processes that twist and fling out matter and radiation. As you fall through the ergosphere, your trajectory is not simply inward. It is bent into a spiral by the rotating geometry. To you, this may feel like an odd, unavoidable twisting of space itself. No matter which way you orient the ship, certain directions of motion are favored, others forbidden. The very meaning of what it is to turn around becomes strange when the background spacetime is being whirled. Eventually, though, rotation or not, the same future waits. Once across the inner horizon in a rotating solution, if such an inner horizon survives the effects of realistic matter and perturbations, the classical mathematics suggests a bewildering interior structure, regions that look temporally reversed, paths that might lead to other universes, even potential exits at white hole singularities. These are mathematical possibilities, most likely tamed or removed by quantum effects or instabilities in any real black hole. The safe statement is simpler. In any solution that includes an event horizon and a singularity, an infalling observer reaches the region where curvature becomes extreme in a finite time. What does it mean, experientially, to hit a singularity? Our language fails us here, because our language is built on assumptions that singularities violate. We imagine surfaces, impacts, forces, a singularity, in the general relativistic sense, is not a physical object you bounce off. It is the end of your world line, the place where your proper time ceases to extend further indoors. Your clock stops not because it breaks, but because the geometry it measures ends. If we could somehow pause just before that end, freeze in a very small region where quantum gravity becomes important, we might find that space-time is no longer well described as a smooth continuum. It might be granular or foamy or replaced entirely by some more abstract structure of entanglement and algebra, rather than falling into a point. You would be dissolving into a regime where the very notions of location and duration lose their meaning. But this is speculation. Our current theories do not yet offer a reliable movie for those final moments. What we can say with some confidence is that, from your own point of view, the journey from horizon crossing to whatever happens at the center is not infinite. It is not an eternity spent hovering at the edge. It is a finite stretch of your life. You could, if you wished, count down the remaining time on your wristwatch, independent of what any external observer thinks is happening. To someone far away, watching your signals slow and dim, you never quite arrive. In their description, your information is accumulated and smeared over the horizon, mixed into the degrees of freedom that later radiate away as Hawking quanta. For you cross, continue, and end. Both stories are faithful within their own domains. Neither can be simply discarded. This duality of perspectives is what makes crossing an event horizon such a powerful metaphor, and such a conceptual trap. We want a single, godlike view that reconciles them. We want to say definitively whether you are really inside or really frozen at the edge. The physics seems to insist that asking for that single view may be asking too much. In some approaches, especially those influenced by holography, the interior region you experience is a kind of emergent space, woven out of patterns in the entangled quantum state that also describes the outside. The horizon is not a simple surface in pre-existing space. It is a particular arrangement of correlations. From that angle, crossing the horizon is less like moving through a doorway and more like shifting which part of a global pattern you can access. The inside is a story told consistently for certain observers, one that cannot be extended to include the entire system at once without contradictions. This begins to sound abstract until you notice the echo at cosmological scales. We live within our own horizons, the most obvious one being the boundary beyond which light has not yet had time to reach us since the earliest stages of expansion. We cannot send signals beyond that boundary and receive replies. For us, it is effectively an event horizon. We exist inside a region whose outside we cannot interact with. We know that any complete description of our observable universe must grapple with that limitation. Thinking about crossing a black hole horizon is practice for thinking about our own position in cosmic space-time. In both cases, there are questions that make sense only from certain viewpoints. For an observer who never leaves the vicinity of Earth, the universe always has a finite age and a finite observable radius. For an imagined super-observer who could step outside our cosmological horizon, the story would look different. If such an observer could exist at all, you can feel the temptation to place yourself in that superposition. To imagine watching not just a person falling into a black hole, but the entire universe falling into something larger, from an outside, that does not participate in the fall. That temptation is exactly the mental habit these ideas are trying to expose. We are not outside the system we are describing. We are inside, tracing world lines, in a space-time that may itself be an interior region of a larger reality. So when we slow down and picture an infalling astronaut crossing the event horizon, we are not just indulging a science fiction scenario. We are testing how far our intuitions can stretch. We are asking whether we can accept a world in which different observers genuinely disagree about what it means to cross a boundary. Yet neither is wrong. We are rehearsing for a more unsettling shift, The possibility that what we call the universe might be an interior, in exactly this sense, with an outside description that never includes us as a completed object, only as a pattern on a surface or a term in an equation. In the end, the story of crossing the horizon is not a tale of drama at a specific location in space. It is a tale of how far causality can reach, of how time and space exchange roles under extreme curvature, of how the same set of events can be organized into different narratives depending on where you stand. The singularity at the end of the fall is a marker of theoretical failure. The horizon you pass on the way is a marker of epistemic failure, a place beyond which some stories cannot be told from outside. Between those two markers, a finite life unfolds, with its own private sequence of moments, its own internal sense of continuity, irretrievably cut off from the distant stars once the horizon is behind. If our universe is in any way analogous to that interior, then our own story may be similarly bounded, complete and continuous from within, yet permanently partial from any imagined outside. If our whole cosmic life plays out inside a horizon of some kind, then the next quiet question is this: when we point our instruments outward, what are we actually seeing? And how close do those images bring us to the edge of what we can ever know? For a long time, black holes lived mostly in equations and thought experiments. The sky did not hand us obvious circles of darkness framed by rings of light. It gave us points and smudges and spectra. It took a change in how we look to turn those hints into something closer to a direct glimpse. Start with the idea of making a telescope the size of a planet. To see fine detail, a telescope needs a large aperture, a wide mirror or dish, because the sharpness of an image is limited by the size of the instrument compared to the wavelength of light it collects. Building a single solid dish as wide as Earth is not possible, but you can scatter many smaller dishes across the globe, record what each one receives, and then combine those signals using the timing information encoded in them. This technique is called interferometry. It is a way of letting the planet itself stand in as the lens. An array of radio telescopes working together this way has, in recent years, focused on the region around a supermassive black hole in a nearby galaxy, and on the one at the center of our own. What they see is not the black hole itself, because the interior cannot send light to us. They see the glowing plasma that orbits near the horizon, emitting radio waves as it swirls in strong magnetic fields. Against that glow, there is a darker patch, the so-called shadow. The shadow is a product of bent light. Rays that pass close to the black hole are deflected, some captured, some sent on looping trajectories that skim around the hole multiple times before escaping. There is a narrow region where light can orbit, tracing almost closed loops in unstable circles. This region contributes to a bright ring called the photon ring. Inside that ring, fewer light paths make it out to distant observers, so the image shows a darker central area. The shape and size of this shadow are not arbitrary. They are predictions of general relativity for a given mass and spin. The theory tells you how space-time bends, how light rays travel, and therefore what silhouette a black hole will cast against a glowing background. When the observations are processed and the blurry, noisy data are turned into an image, the resulting ring and shadow can be compared directly with those predictions. The match is not perfect in every detail. Astrophysical environments are messy. Gas flows are turbulent. Magnetic fields twist. Disks flare and dim. But the broad structure, the size of the dark region in relation to the inferred mass of the whole, the asymmetry of the ring caused by motion close to light speed in the disk, all of it sits comfortably within the expectations of a curved space-time with an event horizon. It is as if Einstein's equations, written on paper a century ago, have left their signature on a radio image drawn across the sky. This does not show us the interior. It does something more limited and more precise. It confirms that there is a region from which light does not escape, surrounded by matter moving in exactly the way you would expect, near a point of no return. It tells us that horizons are not just artifacts of simplifying assumptions. They are features the universe is actually willing to build, where images give us a still frame of the immediate neighborhood of a horizon. Gravitational waves give us the soundtrack. Gravitational waves are ripples in space-time itself, produced when massive objects accelerate in certain asymmetric ways. To imagine them, think of a trampoline. Place two heavy balls on it and let them orbit each other. The fabric wobbles. Crest and troughs move outward from the dance. In general relativity, there is no underlying material sheet, but the geometry of distances and times undulates in a similar fashion. These undulations can travel vast distances, carrying information about their source. The first detections of gravitational waves came from pairs of black holes spiraling into each other and merging. As they orbit, they lose energy by radiating it away as gravitational waves. So they move closer together, orbit faster, and radiate more strongly. The signal picked up by detectors on Earth is a chirp, a rising tone whose frequency and amplitude increase until a final sharp ringdown as the newly formed single black hole settles into a stable shape. From the pattern of that chirp, one can read off the masses of the original holes, the distance to the merger, and the properties of the final remnant. The ringdown portion, in particular, is like the sound of a bell after it has been struck. Each mode of vibration has a specific frequency and damping time that depend only on the mass and spin of the black hole. By measuring those modes, we can test whether the object is behaving like the black holes predicted by general relativity or something more exotic. So far, within the precision of current instruments, the mergers seen through gravitational waves align well with the expectations of classical black holes. The waves tell us that there are compact objects with no material surface, whose mergers release a significant fraction of their mass energy in a burst of space-time ripples, and whose post-merger ringing is consistent with horizons rather than hard surfaces. If there were a solid surface instead of a horizon, some portion of the infalling matter would crash into it and produce a different late-time signal, an echo. Searches for such echoes have, so far, found no firm evidence. Again, this does not prove that the interior is exactly as the simplest solutions say. Quantum corrections, exotic matter, or other effects could alter the deep core without changing the ringdown in ways we can currently detect. But the consistency between theory and observation keeps narrowing the space for wildly different alternatives. It pressures us to take seriously a universe where event horizons are real, dynamical structures, beyond direct detection. We also rely on simulations, these quiet universes inside computers, to interpret what we see. Einstein's equations are compact when written down, but extremely difficult to solve for complicated situations. Two black holes merging, a magnetized accretion disk around a spinning hole, jets punching through surrounding gas. These are not problems you can solve on a napkin. They require numerical relativity, the art of turning the equations into a set of instructions that a computer can follow step by step, evolving an initial configuration forward in time. In these simulations, space-time is sliced into small pieces, a grid over which the metric and matter fields are defined. At each time step, the code calculates how those fields change according to the equations. The result is a dynamic model, how the horizons move, how the gravitational waves propagate, how the gas flows, how light rays would travel through the scene, different assumptions about initial spins, magnetic field strengths, and matter distributions produce different patterns. These synthetic universes are then used as templates. When a gravitational wave detector records a noisy chirp, It is compared against a bank of simulated signals. The best match tells us what combination of masses and spins likely produced it. When the ring around a black hole is imaged, simulations of accretion flows under various conditions are used to interpret the brightness distribution, the variability over time, the thickness of the ring. There is a recursive feel to this. We build models based on a theory, simulate what that theory says should happen, and then use those simulations to decode actual data. It is natural to ask whether we are simply seeing our own assumptions reflected back at us. The reassurance, such as it is, comes from the fact that the same theory has to survive tests across many different regimes. The parameters that explain the inspiral of two black holes must also make sense of the ring down. The same general relativity that shapes the photon ring must also account for the orbits of stars near the center of our galaxy and the large-scale structure of the universe. Those stellar orbits are themselves a powerful clue. Near the heart of the Milky Way, astronomers have tracked individual stars as they loop around an invisible mass over many years. One particular star follows a tight, elongated path that carries it incredibly close to the center. From the shape and timing of its orbit, we infer that there is a compact object with millions of times the mass of the Sun squeezed into a region smaller than the orbit of Earth. No known cluster of normal stars or dark remnants could remain stable in such a small volume. A supermassive black hole is the simplest fit, taken together. These observational threads, shadows in radio images, chirps in gravitational wave data, flares from disks, and stellar dances near galactic centers form a converging pattern. They are all telling us that general relativity's most extreme predictions are not just mathematical curiosities. They show up in real systems, horizons, or something so close to them that we have not yet seen a difference, are part of the cosmic landscape. For the question of whether our universe could be the interior of a black hole, these clues play an indirect but important role. They show that space-time is capable of structures with global properties, regions divided by horizons, interiors that cannot communicate with exteriors, singularities where classical description fails. They show that information can be hidden behind boundaries that we can only infer from their effects. They show that gravity is perfectly willing to arrange matter and geometry into situations where no single observer's description captures everything. What they do not show, at least not yet, is any clean observational signature that would tell us, from inside, that our entire cosmos is living in such an interior. The standard cosmological model, where the universe is treated as a homogeneous, isotropic spacetime expanding from a hot, dense beginning, fits a vast amount of data with impressive accuracy. The cosmic microwave background, the distribution of galaxies, the relative amounts of ordinary matter, and dark energy, all of it sits comfortably within that framework. Black hole cosmology ideas, the ones that suggest our Big Bang might be related to a bounce inside a higher dimensional collapse. We have to reproduce all of that success while adding an unseen layer outside. From our position, inside any such structure, the observable consequences may be subtle or even entirely hidden. The analogy between a black hole interior and our universe may be more about structure than about measurable detail. In other words, observationally, we are in a familiar position. We have strong evidence that horizons and interiors exist in the universe we can see. We do not have evidence about whether our universe itself is an interior in some larger construction. The data press us toward accepting the building blocks, the behavior of space-time near strong gravity, the reality of black holes, and leave the larger scale questions open. The images, waves, and simulations do something important. Though, even in that uncertainty, they make it harder to dismiss as purely fanciful the idea that global structures like black holes could play a role in cosmology. They remind us that we live in a universe where empty words like inside and outside are complicated by horizons and dualities. They show us, with increasing clarity, what it looks like when gravity bends the stage so much that the audience and the actors can no longer agree on where the edge of the stage is. From here, the path leads not toward sharper photographs or cleaner waveforms, though those will continue to refine our picture, but toward a different kind of frontier. The limits of what any observer inside a system can know about the system as a whole. That is where the question of whether our universe is inside a black hole finally turns from speculation about exotic objects into a mirror held up to our own position in the cosmos. If we can never step outside the system we are trying to describe, then any claim that our universe lives inside a black hole has to face a quieter, harsher test. Not, is it dramatic, but where does it actually fail? And what kind of truth, if any, does it leave behind? And one of the first challenges is brutally simple. If our cosmos were literally the interior of a black hole, you might expect to find some clear outer boundary in our equations. Something like a cosmic event horizon enclosing everything. We do talk about horizons in cosmology, but they are not the same as the horizon of a black hole sitting in an external space. A black hole event horizon is an absolute border for distant observers. Beyond it, no signal can ever escape to infinity. In cosmology, the most familiar horizon we meet is the distance light has had time to travel since the hot early phase. That boundary marks how far we can see into the past. Not a surface in space where the universe ends. In some models with accelerated expansion, there is also a true cosmic event horizon, a limit beyond which events will never influence us no matter how long we wait. But we do not observe that horizon as a glowing shell or a sharp edge. It is a feature of the global geometry, not a detectable wall surrounding a contained interior. This difference matters. When we say we are inside a black hole, in the ordinary astrophysical sense, we imagine an exterior region where observers can circle the horizon, watch things fall in, and never follow. For our universe, there is no such confirmed outside vantage point. We do not see ourselves as a dark patch in someone else's sky. The analogy, already, is incomplete. There is another, more geometric objection. The standard description of our universe on large scales is that it is remarkably uniform. Look in one direction and then another, at the same cosmic distance. And the statistics of what you see are almost the same. This is called isotropy, the property of looking similar in every direction. Combine that with homogeneity, the idea that on very large scales, every region of space looks broadly like every other, and you get the familiar image of a cosmos that has no special center, no privileged place. The interior of a simple black hole, in the classical solutions, does not share that character. There is a distinguished center, the singularity, and the geometry around it is not the same in every direction. The radial direction, the direction toward the singularity, is not interchangeable with directions tangential to it. If you tried to identify that radial direction with something like our cosmic time, you would find yourself twisting the theory into shapes it does not naturally take. There are more sophisticated constructions, based on higher dimensional models and more exotic solutions, where parts of a black hole interior can mimic an expanding, nearly uniform universe for a while. Those are the seed of many black hole cosmology ideas. But they are not exact matches, and they often require delicate choices of parameters or matter fields. The resemblance to our cosmos is suggestive, not compulsory. Dark energy deepens the tension. Observations indicate that the expansion of our universe is accelerating. Galaxies on very large scales are not just moving apart at a steady rate, the rate itself is increasing. To account for this, cosmologists include a component in the equations that behaves like a constant energy density filling space, or something very close to that. This is what we call dark energy. It is not dark in the sense of being black or hidden behind horizons. It is dark because it does not emit or absorb light, and because we do not yet know what kind of field or mechanism underlies it. Classical black hole interiors are not usually dominated by this kind of smooth, repulsive energy. They are dominated by the crushing pull of collapse. There are spacetimes, such as ones with a cosmological constant, where horizons and accelerated expansion coexist, and these can be stitched together with black hole solutions in various ways. But making our observed universe fit cleanly onto the inside of one particular black hole, while keeping all the details of cosmic acceleration and structure formation intact, is a technical and conceptual challenge. The analogy resists being made literal. Even the simple fact that we see no global center in our observations is a kind of quiet argument against naive versions of the idea. Inside a star collapsing into a black hole, for example, you can identify a natural center, the point around which the matter is distributed, the place the collapse converges on, our universe. By contrast, looks the same from every galaxy's perspective. Each one can say, with equal right, that everything else is moving away from it as space expands. That is what it means to live in a space without a special origin. Black hole cosmology models have to work hard to reproduce that property. Some succeed mathematically, in the sense that they produce effective descriptions for internal observers who would swear they live in an ordinary expanding universe with no center. But again, the match is not proof. It is a reminder that geometry is flexible. The same underlying space-time can be sliced up and described in different ways, some of which look more black hole-like, and some more cosmological. On top of these technical issues sits a broader worry. To say that our universe is inside a black hole in a higher reality is to stack theories. We take general relativity, which works well on large scales. We add quantum field theory, which works well for particles and radiation. Then we layer on string theory or brane cosmology or some other higher dimensional framework. Then we pick a particular construction in which a black hole interior looks like an expanding region. Each step may be internally motivated, but the final tower rests on speculative ground. This does not make the ideas worthless. It just means we should be honest about their status. They are not extensions of the standard cosmological model backed by overwhelming data. They are exploratory maps drawn in the space of possibilities. They tell us more about the shape of our ignorance than about the definite architecture of reality. And yet, even with all these challenges, the hypothesis refuses to be simply thrown away, because its true value may not lie in being right in detail. It may lie in what it forces us to confront. Thinking of our universe as the interior of a black hole pushes us to acknowledge horizons as fundamental features, not technical nuisances. It reminds us that any observer inside a region bounded by a horizon has access only to partial information, and that this is not a practical flaw but a structural fact. It echoes the way the black hole information puzzle has made physicists rethink the relationship between space-time and quantum entanglement. It makes the question, where is the information about the universe stored, feel less naive, and more like a precise, unsettling problem. It also brings together three strands that often sit in different corners of our mind. Physics, in the sense of equations and predictions. Information, in the sense of what can be known and how it can be encoded. Existence, in the sense of what it means to be something rather than nothing within a world that may not be the whole. Black holes, with their horizons and singularities and holographic shadows, sit exactly at the point where those strands knot together. Seen this way, the black hole universe idea is not primarily a claim about location. It is a lens. When you look through it, certain assumptions you did not know you were making become visible. The assumption that the universe must have a single, privileged outside perspective from which its story could be told completely. The assumption that beginning and end are global, absolute features rather than viewpoint-dependent ones. The assumption that the space we inhabit is the final stage, not one interior region among others. We do not have to believe that our cosmos literally bloomed from the collapse of some star in a higher parent universe. We do not have to commit to any specific higher dimensional brain construction. We can simply let the possibility hang in the air and ask what it reveals about us. About how quickly we reach for pictures that place us at the center. About how reluctant we are to accept that there may be questions permanently out of reach. Not because we are lazy or underfunded, but because of where and what we are. Standing under the night sky, none of this changes the simple sight of stars. Photons still cross immense distances to end their journey in your eyes. The cosmic microwave background still bathes you in a faint, uniform glow from an early, hot phase. The expansion still carries galaxies away, faster and faster, over billions of years. Whether these phenomena unfold in a self-contained space-time or in a pocket carved out by some larger gravitational collapse, your life still occupies its same small span. What shifts, if anything, is the kind of humility that feels appropriate, not the humility of shrinking yourself before a vast, indifferent universe, but the humility of realizing that every story you tell about that universe is an inside story, that you are drawing maps on the walls of a room whose outer architecture you may never touch, that the neat distinction between inside and outside is a convenience in your diagrams, not necessarily a fundamental property of whatever is. So the question lingers, not as a puzzle to be solved tonight, but as a companion. If our universe were the inside of a black hole, how different? Really? Would that make your place in it feel? If this thought stays with you after the screen goes dark, let it. Let it follow you the next time you look up, or the next time you catch your reflection in a window, and remember that you are also something the universe is doing from the inside. And if you want to keep walking along this edge between what we can measure and what we can only suspect come back, bring your questions. And we will keep falling through the dark together, one quiet horizon at a time.